Okay. Hello. Good evening, everyone.
Yes, sir. Good evening, sir.
Good evening, sir.
Okay. I hope all of
Sir,
you are ready for their exam.
Yes, sir.
yes, sir.
Yes, sir. With full
Yes,
full energy, or little bit doubts are there.
Little bit energy from yourself today.
Okay.
Sir, always we are going with a full confidence. Then by seeing the question, our confidence will go down.
yes, sir.
So okay. So the thing is, it might be possible that you will feel that the question paper will be little lengthy. Okay. But don't intimidate it by that. Just think about it. First of all, read the question properly and then try to solve it. Right. Okay. Think in your mind what will be the process you should follow after reading the question. So just give some time to read the question and then only try to solve it. Just don't see the question and directly jump onto, at least for the questions which are numerical type.
Yes, sir.
It's a bit lengthy question paper, I think, but fine. I think the interim also will have 1.5 hours, right, to solve. And depending
Yes, sir.
upon I think how many courses you have taken this term, the time will vary, I think, for all of you. But at least 1.5 hours will be there. That is for sure, right? Okay.
Yes, sir. For every subject, 1.5 hours.
Yes. So what we'll do today is we'll look at only those topics which are important for us for the end term. Okay. I may not be going like whatever I'll discuss. That might be like important for your uh, end term exam. Apart from that, I will not be discussing anything outside it. So if you want, you can ask me if you have any doubts in other concepts. But what I am discussing, that is mostly very important for your end term exam. Is that fine?
Yes, sir. Sir, can you discuss more?
Mock you want?
Yes, sir. But deadline is today.
Deadline is today. Is it
Yes,
over or
sir.
is it there?
No, sir. It's till 11:59.
Then how should I discuss it?
Okay, sir.
But if you have any specific doubts, you can ask me. I can go over that. Any other previous year questions if you want, right? Let me
Yes.
know. I'll solve those also. Fine. Previous
Okay,
year
sir.
questions we can solve. Not an issue with that. Okay, that's fine. Okay. So maybe I'll let me start now. We'll hover through the important questions or important topics which are there from week 11 and 12, right? I assume that all of you have completed till hard margin classifier, and I think we haven't. So I think Nikita might not have completed that week 11 topic, right, of soft margin classifier, right? We'll see that. I will not go through the entire derivation. Rather, what I'll do is we'll stick to the things which might be important for us, right? Is that okay? I hope that is
Yes, sir.
fine for all of
Yes,
you.
sir.
Okay, so let me start it. Uh, okay, my screen is visible, right?
Yes, sir.
Okay, so okay, let me start now. So this is today's session is uh, revision session. To MLT, right? And mostly will be, so what topics we'll see today is soft margin SVM. This is also very important topic as far as your exam is concerned.
The
So
paper is from the first 8 weeks.
what is it?
How much, what percent of the paper is from the first 8 weeks, week 1 to 8?
Week 1 to 8. Okay, right now I don't know exactly what is the weightage, but give me some time. Maybe after the session, right at the end of the session, I may give you the full details about it. Is that okay?
Okay, sir.
Yeah.
Okay.
So soft margin SVM is there, and then maybe the ensemble technique. Which one is there? Which we have seen. So you may encounter the numerical problem on this. So that is ensemble array. in simple method, which one we have seen for this course? It is I think random forest, right? Random forest, and then boosting algorithm, boosting one, which is AdaBoost. So numerical problems can come from these topics. Okay, AdaBoost, and and one more thing is neural network, right? So these are the main topics from week 11 and 12. I'll be just focusing on these four broader topics. Then, if you have any other doubts, you may let me know. I can.
So loss functions.
Loss functions are there, but not like I would say that from your point of view of the exam, right? That might not be important. If you want, I can just explain those also. That is not an issue. So these are the four topics I just which I've written here. They are important for your uh, exam. And see these three, right? You can encounter the numerical problems on these three questions, so three topics. And from soft margin SVM, the theory questions, which is based on your understanding of soft margin SVM, you may find it in the question. Is that okay?
Yes, sir.
Okay.
Yes, sir.
Okay, so let us try to start with the primal formulation of the SVM, right? Soft margin SVM. So, what is the difference between hard margin SVM and the soft margin SVM? The main difference is what? It can accommodate the outliers also, right? Correct, right?
Yes, sir.
Or those outliers, in the sense, when I say outliers, in this case, what do you mean by outliers? The points which are incorrectly classified, or the points which are correctly classified but not with the enough margin, right? Is that correct? So
Yes, sir.
we try to accommodate these points by by what? So how do you accommodate these points? By paying the
Bribes.
bribes, right? So by paying the bribes, and now the uh, the formulation for the optimization problem will look like what? Minimum of W RD, and this is what your we wanted to maximize the width, right? And we have seen the width was uh, 2 by norm of W square. That might not, that is not a standard width, okay? That is like non-standard width. Standard width is 2 by norm W, but that is fine. That's it. We have taken it a non-standard width in this problem or in this course. So it is half norm W square plus what?
C times.
Yeah. So this is the regularization parameter,
Yeah.
and what we do is
One, 1 to n psi I.
right. So these are the bribes, right? These are the bribes which we pay across uh, any examples. So not every point need to pay the bribe, right? Only those those points. Okay. Mock, I think it is not. The deadline is not over, right? So, but still, if you have any specific doubts, right, you let me know. I'll just try to explain it. And such that what? So is not mock is covered in the TA session? What is covered in TA sessions?
Sir,
Uh,
please ask you.
yeah, and P5Qs.
Any other TA session is there tomorrow or uh,
No.
No, sir.
So no session for tomorrow. Today is the last session.
okay, fine. Okay, let us see like how much we can accommodate into the session. Okay, so okay, what are the constraint here?
1 minus W transpose.
Or the general constraint is what? W transpose
W
xi
transpose Xi.
yi plus now the
Yeah.
bribe, right?
Plus
Plus the bribe, it
is
should be
greater than or equal to 1.
right. So if uh, and this is for all i's, and what else? And each of bribe, right? Epsilon I should be what?
Greater than or
greater than equal to 0.
So these are the two constraints, right? So this is my objective function of the optimization problem. These are the two constraints, and these are both of them are the inequality constraint, right?
yes, sir.
Correct. So this is the formulation for the primal problem of a
Soft
soft
margin
yes,
principle.
yes. So how to solve this problem, right? So what you do first, you can actually find out its Lagrangian. So how to write its Lagrangian? So Lagrangian will be uh, the function of w epsilon,
Alpha, beta.
and will be a vector, right? W is a vector.
Yes, sir.
Psi also is a vector, right? It's what it will contain all the bribes, and wherever any point if it does not pay the bribe, it will be zero for that, right? So what do you think the if psi epsilon or psi, right? If it is a vector, what do you think its dimensions should be? Is it d dimensional or n dimensional?
D, sir.
Sir,
D?
for W,
No, no, epsilon.
Sir, any isn't it n?
Yes, n cross 1, right? That will be the n cross 1. But W will be
D.
d cross 1, right? Okay. So let us say, okay, some noise is coming. Can you just, I don't know from where it is coming. Please try to go at some place where you can, the noise will be minimal. Fine. So, okay. How should I write this Lagrangian? I should write this function first, the objective function first. That is half norm of w square plus c I equal to 1 to n epsilon I, and this is greater than or equal to, right, and this problem is minimization. So how to make it equality constant? Alpha times what?
1 minus W transpose.
It will be, let's say, if I just write in terms of uh, summations, it will be summation across all uh, i's, and it is going to be what?
Alpha
Alpha I
times
1
1
minus,
minus G of W, which is
yeah, so g of w is basically here
is
it is
constant, yeah.
xi yi and minus,
Epsilon I.
right, and plus summation across all the n's is beta I into,
Minus epsilon I.
is that okay?
Yes, sir.
This is your Lagrangian, and you can say that it's a primal problem, right? To
Yes.
uh, you know to minimize over this w and epsilon, and its dual problem will be what? So basically I can write this minimization problem as like this now: minimizing over w and epsilon, uh, and maximizing over
Alpha
alpha
and beta.
beta is half norm w square plus c summation of I equal to 1 to n epsilon I plus summation of I equal to 1 to n alpha I into 1 minus w transpose xi yi, uh, sorry, and I think it is
Epsilon I.
minus epsilon I plus summation of I equal to 1 to n beta I into minus epsilon. This is your primal problem, right? This is the primal problem. This is your primal problem. So what will be the dual problem? So the dual problem will be, and this is equivalent to the dual problem. So you are basically converting the min max problem into maximum problem, and that is what dual problem is, right? So max of alpha comma beta, and minimum of uh, half norm w square plus c times summation of I equal to 1 to n epsilon I plus summation of I equal to 1 to n alpha I 1 minus w transpose xi yi minus epsilon I plus summation of I equal to 1 to n beta I minus Is that correct? That's fine.
Yes, sir.
So this is your dual problem. Okay. You should remember this. At least you should know, if you know this right, you can actually formulate it by using Lagrangian and this dual problem. Okay. Now, what we have achieved from this? If I try to solve this problem, uh, what should I get? So the dual problem solution will be what? Okay. I think in between, let's try to understand first what are the things you should get, right? If I fix alpha and beta and you differentiate with respect to W and differentiate with respect to, uh, if I try to solve this problem, right? That means I'm trying to solve this inside bracket, right? This bracket I'm trying to solve. And what will be the solution, or what I'll get it? Let's say I'll get the W star as, by fixing alpha and beta, right? By fixing alpha and beta, I get W star uh, as summation of I equal to 1 to n. What is it? Alpha I
XI, YI.
say yi. Okay. This is my primal solution, right?
Yes, sir.
Our solution to primal problem, but we have get it from what? Or in terms of this is in terms of algebra. This is algebraic format. If I wanted to see it in the uh, vector format, how that will look like? This
XY alpha.
xy alpha. So this is my vector format, right? This is algebraic and this is vector. And how do I get that? So if I this Lagrangian, if I differentiate with respect to w and equate it to 0, this is the solution I get. This is obviously by fixing alpha and beta. And if I again, if I there are two, right? There are two variables, w and psi,
Epsilon.
right? Yeah, or epsilon, right? So and if I equal it to 0, what I'll get here? I'll get alpha I plus beta I equal
Equal
to,
to C.
right? This is important thing in our discussion, right? So this is equation 1, this is equation 2. These two are the important things. And now our problem will become what? The dual problem will become like this: max of alpha. Alpha again should be greater than 0. Why alpha and beta greater than 0? They are the Lagrangian multipliers, right? So
Yeah.
be positive. And what else? The condition is alpha
Plus beta is equal to C.
equal to c. So right. So that means it is bounded between this, right? Okay. Fine. That is okay.
Sir, for any number of Lagrangian multipliers, this condition holds true that
Yes.
it should be
So
positive.
this alpha is actually a vector of Lagrangian multipliers, right? So if
Yeah.
you think about it, when I just say alpha I, right? So that means I will have how many? N number of Lagrangian multipliers here, and beta also with n, right? So everything, for every alpha, it has to be greater than 0, greater than equal to 0, for beta is greater than equal to 0, and alpha plus beta equal to C. Is that okay?
Yes.
Now alpha transpose, and that probably will become alpha transpose. One is the identity matrix, and or identity vector, right? So all ones, half alpha transpose. So this is like not very important, but I'm just writing it down.
X transpose X Y alpha.
Right. So if you don't remember this, that's not a problem. So since this condition is there in the constraint, what we have done is we have included that, and now our solution has become max of alpha greater than equal to 0, beta greater than equal to 0, alpha transpose 1 minus half, what is it? Alpha transpose y transpose x transpose x and y alpha. Is that okay? Fine. So now this problem, right? This problem, if or this solution, right, to the dual problem, that is kernelizable, right? Because we can see the kernel matrix here. So this is kernelizable. That is fine. Now the important thing are actually starting from here. So one more thing is that, okay, sorry, I think I have done the mistake here. So all the constants I can write like this, right? So alpha is bounded by two values, which is what? 0 and c. These are called as the box constraints. Okay, that's fine.
Sir, what is alpha
Alpha is the Lagrangian multiplier, right?
and what is C?
C is the this thing, right? So the parameter which we actually using it for the penalties, right? So we don't
Okay,
want
okay.
these penalties to grow very large. So that's why we are actually keeping a tab on that, right? And how should we do? So these are the penalties, right? So
Yeah, yeah, yeah.
maybe I'll just draw the diagram.
Yeah, yeah, yeah. Draw the diagram and please explain.
Yeah. So let us say uh, this was your uh, okay. Um, suppose this is your hyperplane, right? Which is your W. So what is this hyperplane? It is W transpose x equal to
0.
0. The supporting hyperplane will be what? Let us say, okay, let us say the supporting hyperplanes are this. Okay, that is okay. This W. Now, what are the equations of the supporting hyperplane? It is W transpose x equal to 1, and here this W
Minus.
transpose x equal to minus 1, right? Or you can write it as like this yi, right? So if you understand it, W transpose xi or x into y
Uh,
equal to 1, right? But it's okay. I can write minus 1 to so it is minus 1. That means it's a uh, negative.
Y is the label for that minus
Yeah,
1.
so it's a negative class, right? So suppose these are the positive examples, right? So they are all positive examples, right? Okay, the red denotes the positive values, a positive class. Red is positive class. Right? So this point is on the hyperplane. So this point is there. Now this point is there. This point is there. This is negative. Okay. Okay. So I hope all the points are visible.
Yes,
Okay.
sir.
So, which of the points will actually pay the bribes? What do you think? So, we said, or which are the points we call them as outliers? The points which are not correctly counted
Misclassified or
or
are
classified
even
correctly but without
private. Yeah.
correct.
Okay.
So, can I say that this point should pay the bribe?
Yes.
Yes,
Yes, sir.
Yes. This point should pay the
Yes.
bribe.
Yes.
This point should pay the bribe.
Yes.
yes,
Then this point should pay the bribe.
yep,
Yes.
This point should pay the bribe, and this point should pay the bribe. Is that okay?
Yes.
yes,
And according to our problem or formulation, what we are saying that we are actually checking with all, right? Summation of I equal to 1 to n epsilon I, right? Correct.
yes.
So for other points, right, which are correctly classified, they should they pay the bribe?
No, no.
No.
Right. Only this circled with the blue, right? They should pay the bribe. Okay. But how do you decide that how much? So let's say let's take this point. How much bribe? Okay. This point should pay. So the minimum bribe it should pay is this one, right? So that it can
Yes,
get correctly classified with enough margin. But in the for so if I pay this bribe, this much bribe, is that fine?
no, no.
No.
No, no. But in general, if I pay the larger bribe, still it will be correctly classifying, right?
Yes, it's
Yeah.
correctly classified, but there's no need.
Yeah.
We,
Yeah.
Okay. So how will you mathematically how will you say that? So you should uh, put a cap, right? So if you are paying like extra bribe, right, the value of C it will make it down. Is that okay? So you should
okay.
so collectively it should all of them ideally how much they should pay, only this much, so that they can actually, let's say this point should pay at max this amount of bribe, right? This point, uh, this amount of this point, only this much, like that, right? But in the mathematical formulation, how should you check that, or how should you keep the tab? Because currently this mathematical formulation says I can actually pay any bribe, right? But since
Yes.
this is a minimization problem, right? It should be minimum. It should be as minimum as possible. Then what you are doing, that C is kind of you can think of as a vector now, let's say, right? And it is multiplying. Let's say it is C1 epsilon 1 plus C2 epsilon 2 plus C3 epsilon 3, and it will go until Cn epsilon n, right? So this equation I'm writing down here, right? And C is what? Like all C1, C2 to Cn, right? And similarly, so this, right, this summation should be as low as possible. You can think of them as a weights, right? So we are learning those weights by minimizing this, right? So
So, what is this xi thing?
it's a bribe, right?
So xi is bribe and C
So actually, this
C.
epsilon one, right, is a standard bribe you can think of, right? Or and we are actually scaling it. Fine.
Okay. I'm not able to understand. Like, if this is the bribe, then what is C actually doing?
C1 is kind of weight. Let's say C1 epsilon one, right? Okay. Let's say
C is like constraining not to pay much bribe than the expected.
Okay, okay,
so
okay, 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 okay,
you
okay,
cannot go like beyond some value, right? So you are actually saying that this product has to be should be within this limits,
okay, 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 okay,
right?
okay, okay.
So if I just have epsilon 1, right, it will not automatically understand that part, right? So you are actually learning that those parameters basically, right? So it's kind of a hyper parameter you can think of. Is that okay? In terms of the data you think of it. Is that okay? Now that is okay, right? Okay.
Yes, sir.
So C can take any values between 0 to infinity, right? Okay.
Yes.
So epsilon, if it is lesser, right, it is very less, then you should multiply with the larger value of C, so that it will become like it will become adequate, right? And if C is or if epsilon is very large, what should you have? Because this product, right, C and epsilon, if C is, or if epsilon is very large, C has to be
Very low.
lesser. Yeah, and if C is or epsilon is very low or very less, then C has to be larger, right? So that flexibility actually we are getting by addition, by the addition of this C. I hope you are understanding this part. Hmm? Okay, so we can have C between 0 and infinity, right? So let us analyze let us analyze two extremes here. So if your C, if your C is equal to 0, okay, if C is equal to 0, what will happen?
We won't have to pay any bribe.
That is okay, but in mathematical terms, let's say alpha plus beta equal to C, right? Alpha plus beta equal to C. We
Yes,
have seen
Yes, sir.
these are the complementary slackness conditions, right?
Yes.
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 So alpha plus beta equal to C, and if C is equals to 0, uh, okay, in that case, okay, maybe we shouldn't use this one right now. That is okay. C can be between 0 and what altercations you can actually think about is, uh, if C is equal to 0, what can we say? Can we say that alpha equal to 0?
Yes, we can.
How? Okay. Are you able to understand how we can say that alpha equal to 0 then?
Yes, yes.
Yes, sir.
Why it is
So
equal to 0?
because this equation doesn't depend on the beta parameter.
Not like that, right?
The equation would be alpha plus beta equal to 0. You can't say that.
Alpha is always greater than equal to 0. If C is 0, alpha has to be at minimum, at the best, it has to be. It cannot be negative, no? So alpha has
It
to be
cannot
0.
be,
0
yes,
is
it
less
cannot be
than
0,
alpha, less than C.
right? So if C is equal to 0, that means it's actually it is based on this condition, right? Because alpha is between 0 and c, correct? So alpha should be between 0 and c, and if your c becomes 0, right, then what will happen? Alpha has only one value to take, right? That is equal to 0. Is that okay?
Yes, sir.
Right. So now this constraint actually is based on this constraint, and then that means alpha becomes 0,
And
and
beta is also 0.
yeah. So beta actually we don't right now we
You
don't
don't
care
require
about.
it.
Yeah. So what about W star? So W star is what? It is X alpha or XY alpha, right? Or alpha star. So if alpha is 0, then W star will be
0.
so it will be a 0 vector. So if so what does that mean? So can we say that okay, W star is what? Is a linear combination of these, right? Data points and alpha, right?
Yes, sir.
Or,
Data
or,
point.
or linear combination of data points, right? By looking
Ye-
at it. So what does that mean is alpha equal sorry if alpha equal to 0, that means those data points are not contributing towards W, right?
Yes, sir.
Contributions of the data points in finding out the W, right, uh, which is the important thing, right, for us to classify those points. There is no contribution from this data points at all. Okay, let us say in the second extreme, right? Let's say what is the second extreme? If C is
Z-
infinity, what will happen if C is infinity? If you look at this, then if you think about this problem which I've started, if C becomes infinity, what is the
Then
second one?
it will be hard margin
Right? Why it is hard margin?
Yes, sir.
Because
because
we need to
it's not
minimize, right?
forgiving.
Yeah. So actually it is penalizing all this, right? So that means all the data points are actually correctly classified, and in that case, this will become the hard margin classifier. Hard margin is when all data points are correctly classified. Is that okay?
Yes, sir.
Yes, sir.
Fine. So okay, what are the complementary slackness condition in this formulation?
Can you go down once again? If C, can you re-explain the C is equal to infinity?
Okay, if the C becomes infinity, right? What does it mean? That means you don't have to pay the bribes, right?
Correct.
Correct. So if you are not paying the bribes, what does it mean? The data points are correctly classified, right?
Correctly classified. Right.
So when you pay the bribe, when the data points are not correctly classified,
Not
right?
correctly classified. Right.
And if you are not paying any bribe, that means what? If they are correctly classified, and if they are correctly classified with enough margin, then that
That's
problem
a hard
becomes
one.
a hard margin classifier.
Correct. Correct.
Correct.
Okay.
Okay. So now come to the complementary slackness conditions. From there, we'll actually. So what are the complementary slackness conditions? What are those? So whatever the constraints are there, right? We need to make them equal to 0, right? These two are the constraints, and we make them 0. Complementary slackness conditions will be what? Alpha I into 1 minus W star, or okay, or W star transpose xi minus epsilon I equal to 0. This is the first complementary slackness condition, and the next one is beta I into minus epsilon I, right? Say, and what are the primal solutions here? W star and
W star and
epsilon star, right?
yeah,
And what are the
Yes, sir.
dual solutions?
Alpha and beta.
alpha star, beta star.
Alpha and beta. Okay.
Uh,
Okay. Now let us from these things, right? We have different cases because we know that alpha is actually bounded between
0
uh,
and C.
0 and C. One more relation we know is alpha plus beta equal to C, right?
C.
Let us try to understand all of that, and we'll try to connect with the complementary slackness also. So let us say what is the first, let's say one condition is if alpha star equal to 0, alpha I star equal to 0. For any particular data point, if the alpha I star equal to 0, by looking at the first equation, what do you think about it then? then that means what?
G of W is less than or equal to 0.
Right, so
Less
that
than
also
0.
is there,
Yeah.
not less than or equal to 0. If this is 0, then it has to be it should be less than or equal to 0, correct. And from this, what you can get from this condition, alpha plus beta equal to c. If alpha is 0,
Beta equal to C.
Yeah, beta
beta
equal.
is r equal to c, right?
C.
Right, and if beta is star equal to c, that means it is a positive quantity, right? Because c is positive. So that means what happens to
Psi
this?
is zero. Psi is zero.
Yeah, so can I write this as like plus only, because that is also fine, right? Okay, I did it. Now equal to 0, right? If what,
Sir, explain how to say psi equal to
so
0.
let us say if beta is positive, right? So this quantity is greater than equal to 0.
Yes, sir.
So this quantity has to be 0, right? So that the right hand side will become equal to 0. So let's say if I
Okay.
say 2 into c equal to 0, right? Then what does it mean?
Then
C
C
has to
equal
be
C
to
has to
0
be
to.
equal to
C
0,
is
right?
equal to 0.
Otherwise it
yes,
is
sir.
not possible, right? Then how does the left hand side will become equal to right hand side? So from there we can say that epsilon star equal to, or epsilon I star, it has to be 0. But what does that again mean in terms of
This
the,
means that all the points beyond the, it should be on the right side of the hyperplane or beyond it.
or
Rightly classified.
yeah,
Rightly classified.
yeah. So if I put this
Sir,
value in this first complementary slackness condition, alpha is equal to 0, right? And this, then this has to be greater than or equal to 1, right?
Correct.
yes, sir.
Right, because
So
okay,
W transpose XI1 is equal to epsilon.
so w star transpose xi yi star plus epsilon I star, it has to be greater than or equal to
1.
1,
1.
right? And if epsilon star equal to 0, that means w star transpose xi yi
Is greater than or equal to.
greater than or equal to 1. What does that mean? This
It's
condition
on the
means,
It
hyperplane
means
or
strictly
ahead of
classified
1.
high.
so this is
Rightly
your
classified.
w star, and if this is your hyperplane, and this is your supporting hyperplanes, so the points which have alpha equal to 0, where they will lie,
On the hyperplanes or beyond that.
right? So w star xi yi is greater than 1 for what points? All of those points, right? This side and this side, fine.
There, for the point that lie on the decision boundary, why is alpha greater than 0 and less than c? Why is it not 0?
What is it? Sorry, I don't understand.
I'm
Just give me a
saying
minute.
that that
One
any
minute.
point
Hmm.
that
One minute. One
any
minute.
okay.
Okay, so understand. This is fine. Yeah. What is your question?
Yeah, I was saying that for the point that lies on the boundary, why is alpha's value in the range 0 and c? Why is it not 0? I'm saying this.
It okay. That we okay. Anyway, we'll discuss it. But right, okay. I'll tell you everything like how what that value should be. It can be 0. See, it's not like we cannot say that they are not equal to 0. So currently, you can see that, right? When alpha equal to 0, this is possible for which of the points? The points which are like
Yes,
in this side or this side, or they are on this line also, right?
yes, yes,
Correct, because it is
yes,
greater than or equal to 1. When I say equal to 1, that means they are on this supporting hyperplanes as well. Is that fine?
yes,
Okay, so right now we understood that the points which are correctly classified and the points which are on the supporting hyperplanes, they will have alpha equal to 0. Is that okay?
yes, sir.
Okay, now let us see the second case. We can have three cases, right? What will be the second case? Alpha I is it between
0 to C.
0 to c, and not including the values of 0 and c, fine. So that is like any positive value but not 0 and c. What will happen in that case? So from the second or rather from the first complementary slackness condition, what you can say about this is going to be 0, this quantity, correct? Because if alpha is positive, that means this quantity 1 minus w star transpose xi
Yes, yes.
has to be equal to 0, right? So
0.
one thing I can write down is 1 minus w star transpose xi yi minus epsilon I should be equal to 0, right?
Yes.
Now anything we can say about this? So if alpha is between 0 and c, the condition I know is alpha I plus, okay. So alpha I plus beta I equal to c, right? From that, if alpha is positive, what does that mean? Beta also is in between,
0 to C.
right? So beta also is in, uh,
0 to C. Both excluded.
yeah, both excluded, both extreme excluded, and it should be 0 to c. And if this is true, then what happens to the complementary slackness condition to epsilon I star equal to,
0.
right? Is that correct? So this condition implies that epsilon I star, or let us say, it has to be equal to 0. And if this is 0, if I plug in here, what will happen then? W minus W star transpose xi equal to 0. In another words, W star transpose xi equal to 1. So this indicates which points
On the hyperplanes.
on the supporting hyperplanes, right?
Yes, sir.
So all the points, uh, so this is W star, right? And this is what, uh, sorry, supporting hyperplanes. So the points on the supporting hyperplane which actually are contributing to, so when alpha is positive, what does that mean? I know the equation of W star is what? It is
X by alpha.
equation of I equal to 1 to n x, or okay, or alpha I xi yi, right? So if alpha, so that means if alpha is the positive quantity, what does that mean? The data points which will have the positive alpha, they will contribute to what? W star, right?
Yeah.
And those alpha I star which are actually on the, or if they have the positive value, they are lying on what?
Supporting hyperplanes, so they
Yes.
might be the support vectors.
And they are the support vectors actually, right? So right now in the first two conditions, right, what we have observed, the points which are not or the points which are correctly classified by the supporting hype, or by our W star, they are actually not contributing to W star, right? And they will have alpha equal to 0. The points which are on the supporting hyperplane, they might have alpha I star equal to 0, or they have alpha I star equal to, or in between 0 to c. So the points, those which are on the supporting hyperplane, which will have the positive alpha, they are the support vectors, right? If they have alpha equal to 0, they are not the supporting vector. Is that okay? These
Yes,
two
sir.
conclusions are okay, right?
Yes.
And what the third extreme condition we can have? uh,
I think that answers, bro, you have raised a question, na?
yeah, yeah, that is what
Yeah,
the,
yeah.
Yeah, your question is now answered here, actually.
right? No, now it is clear, right?
Yeah, yeah. Understood, understood. Yeah.
So the points which are on this hyperplane, they might have alpha equal to 0, or they might have alpha greater than 0. The points which are actually having alpha equal to 0, they are not support vectors.
They are not supported. Yeah, this is the answer. Yeah.
The alpha is those points which are having alpha greater than 0, they are the support vectors. Is that okay?
Yeah, yes, 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 sir.
Any positive alpha value is basically between 0 C, 0 C excluded are support vectors
Correct. And they are actually contributing to your
contributing to the, yeah, W star.
now the,
Like, why we are actually considering that equality sign in the first condition, that W transpose X I Y
because
greater than. to 1.
This one
First condition, like,
here.
yeah, 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 this, yeah, W transpose X, Y, Y, I greater than equal to 1. Then why we are considering this equality sign here, if there is a different condition for that?
So here, see, the thing is, when you say alpha s are equal to 0 and beta s are equal to c, right? In this case, okay, I think
Because if it is equal, then alpha I shouldn't be equal to 0. It should be between 0 to 0.
so see, okay, I understand. So let us say, what about this? So let's say if alpha is 0, right? What about this quantity then?
This portion is non-zero.
This quantity
Yeah,
is
greater than equal to, yeah.
greater than
Yeah,
0 or
yeah,
equal to
Yes.
also 0,
Or
right?
equal to.
This also is positive, right? This also is
Correct.
possible, right? Do you agree with this part?
yeah, yes,
Huh? So when
yeah,
I say 1 minus W star transpose xi yi minus epsilon I
Is greater than
is
equal to
greater
0.
than equal to 0. In other words, can I say that it is W star transpose xi yi minus epsilon I should be greater than equal to 1?
To 1, correct.
yeah.
Or sorry, I think it is plus, right?
Plus 1.
The- And that is what I have written here, right?
Hmm.
Now, is it clear?
Equation wise, I am agree with you, sir. But my question is that there is equality sign. So if it is equal to 1, then alpha I will not be equal to 0.
If it is equal to 1, you are saying,
Yeah,
okay, let's say this is equal to 1, then
yeah.
no, then also alpha I can be 0, right? So 0 into 0 is possible, right? 0. Okay, let's say if this quantity is equal to 1, right? If this addition is equal to 1, right? That means 1 minus 1 equal to 0, and if alpha I can also be 0, right? 0 into 0
Mhm.
can be equal to 0. See,
Yeah,
when we'll get 0 into positive equal to 0, 0 into 0 also equal to 0, and 0 into negative also is equal to 0, right? That's okay.
Correct.
But this is not the question right now. This is not possible, correct? Only these two conditions are possible, and I am just taking these two conditions. Okay. Is it okay? Still, I think you'll think it right later on. I don't know whether you are satisfied with the answer right now, but if you think it like little bit later, you might be able to understand. I understand what is your confusion. Your confusion is why I am taking it greater than equal to 1 here and not
What
equal
then?
to.
What is the statement for this? Like, means the points which are on the hyperplane.
Hmm.
What will be the statement for this?
So in this case, if
Yeah,
you have this
equal
greater
to
than
1.
equal to 0, right? That
Yes.
that means I am coming to the conclusion that this is greater than equal to 1, and now since alpha equal to 0, that means beta equal to c, and then epsilon equal to 0.
Yes.
What I am saying is xi by I, right, greater than equal to 1. So where are these points lying? Which are the points? These are the points, right? Xi and yi, with the positive label and the negative labels. And greater than equal to 1 means which which side? All they are correctly classified, right?
Correct.
The meaning is they are correctly classified with enough margin. And when they are greater than 1, right? Where are they? Greater
The
than 1, like they are not on the supporting hyperplane, they are away from the supporting hyperplane and correctly classified. But
yes.
the moment I say it is greater than equal to 1, equal to 1
Equal.
are where? On these lines, right? On the supporting hyperplanes. So the conclusion here is the points which are away from the supporting hyperplane, correct, and
Mm.
which are on the supporting hyperplane, they will have alpha equal to 0. Is that okay?
Yeah.
Okay. The next step, what we say is if alpha is positive, right? Where are those points are lying? They are lying on the supporting hyperplane, right?
Yeah.
So now, what are the if I just include this tool,
Okay, okay. Both condition can apply on the hyperplane. Okay.
correct, right? So that means the points which are
On
on
the
the
on
hyperplane
hyperplane,
can have
alpha can be 0 and alpha can be 0
yes.
or
So
bit
yeah,
different.
so if alpha equal to 0 for the points which are on the hyperplane, they are not contributing to my W star,
Yeah.
right? And if alpha is greater than 0, they are actually contributing to my W star. And
Okay.
and those points which are contributing to my W star, we call these points as what? The support vectors. So if I say that if the point is on the supporting hyperplane, so can I say that that is not necessarily be a support vector, right?
Yeah, yeah, got it, sir. Got it.
Unless it is contributing something.
So
Yeah.
it's like, all points, all the support vectors lie on the hyperplane.
Hyperplane
Well, all the points lying on the hyperplane are not support
cannot
vectors.
be support vector.
Yeah.
Yes,
And the
yes,
reverse is not true.
yes,
Because some alpha is equal to 0.
yes.
Those will
Right.
not consider as a.
Now is that okay?
Yeah, yeah, fine. Fine. Thank you, sir. Got it.
So now the third condition, third extreme will be what? Alpha I star equal to C, right? We have seen first condition as alpha I star equal to 0. Second is alpha I star is between 0 and C. And the third is alpha I star equal to C, exactly C. So in that case, what will happen to my complementary slackness first condition?
Beta is equal to 0.
First thing is, uh,
Beta is 0 means epsilon have happened, means there
no,
is a
no,
positive bribe.
alpha is greater than C is beta is 0. Okay, that is fine. Okay,
Yeah,
that is
beta is
second
0 means
condition.
epsilon is not 0. That is a positive bribe.
Yeah.
Okay. So okay, so that side, from that side, what we can say is because alpha I star plus beta I star,
C means beta I star is 0.
beta I star equal to C, and then in that case,
Beta
beta
is
I star, and sorry, that means beta I star equal to 0,
0.
right?
That means epsilon I is equal to psi I is equal to non-zero,
And
is
psi
greater
I
than
is
equal
equal to
greater than equal to 0.
Greater than or equal to 0.
right.
So you are paying a positive bribe.
This is complementary slackness 2, but what from the complementary slackness 1 condition? What is it? Alpha is greater than is positive number. That means this quantity. Can you say that it should be equal to 0?
Yes, sir.
Is it okay? If
Yeah,
it is
this one is
positive, then this has to be 0. So what is that means? 1 minus W star transpose xi minus psi I should be equal to 0.
Yeah.
Or I can say that epsilon I star is equal to then 1 minus Wi star transpose xi is this, right? And if epsilon I is greater than or greater than equal to 0, can I say that then 1 minus W
W
star
transpose
transpose xi should
greater than
be
equal to 0
0? In another words, I can say that W star transpose xi
is greater than equal to 1.
1. So what does it mean? Where are these points?
These are the points, on the hyperplane,
I think
on
I've
the
done.
right side
I think I've done that
and beyond it.
wrongly.
Yeah, yeah. Some mistake is there. This is the first condition.
1 minus this one equal to 0. Uh,
So you
W,
multiplied it wrong. Yeah.
then it has to be like less than or
Less
equal,
than equal to n. Yeah.
Sorry, less than equal to.
right? Yeah. So yeah, that is also the case. Fine. So where are these points are lying? So this case, if this is W star, right, and these are the supporting hyperplanes, what do you think the points will lie where?
In between.
within the margin. It will lie within the margin.
Not only within the margin, but it can be also on the wrong side.
Yes, right. So, okay.
Both
So,
Both will satisfy this, no?
mm, okay. So the region between this, right?
margin.
Can you say that the region is between this? And
Yeah,
now
yeah.
let us say if the point is this one. Okay, I think I'll use the colors which we have used previously. So I think I have used red color for the positive side, right? Positives are red, negatives are green.
Green.
Okay, so if the point is here, right, and if the point is mm, here, if the point is here and the point is here, right, all of these points uh, which are incorrectly classified or correctly classified without enough margin,
Correct. We all come under this.
this, and they will have what,
Will
alpha is
contribute.
equal to
C.
c, so they will pay the
Right.
bribe, right, and you can say that it might be the highest one, right, because c is the extreme case of or uh, correct, right? I think this is fine, right? No issues with that.
But you
Yeah,
can
yeah.
any point which is beyond,
Hmm.
any red which is going in this side, whatever. Yeah, red going beyond the margin.
Hmm.
Yeah, and you put a red there.
Sure.
So
Okay,
that will also come under this.
that also has to come under this, right?
That also come under
Yeah,
this.
because okay, here you are saying, right, that
Yes, yes.
also will become, because that also have to pay bribe, right?
Pay the bribe, right.
So that also has to come on this side first,
Sir, what
because
about the one
because
on the
for that
hyperplane?
point also this is less than or equal to minus. Huh? See,
Any point
okay,
on the hyperplane, sir?
yeah, I'll tell you. Okay, I'll tell you. The what is this means? It is misclassified points, right? All misclassified points and classified correctly,
As correctly, but violating the margin
correctly,
conditions.
but margin is
Margin is not
less than or
controlled.
equal to one, right? Not
Yes.
enough margin, or
These two conditions actually.
yeah. So if your red is here, right? If red point is on this plane, uh, does it have alpha equal to c? Yes, right? Is it okay?
Yeah.
Yeah. Yeah.
Right?
Similarly, any green on the other side also it will be
Yeah.
same.
So like that. Yeah. Okay, I gave only one example, but
Yeah, you
like
can put one green there.
that's
Yes,
fine.
and
So
one
all
green at the other side.
yeah, that's like yeah.
Correct, correct,
So,
correct.
so basically, the understanding here is what, the misclassified points and not correctly classified, they'll have to give the
Right.
highest bribe.
Nice.
Right? It is C.
Correct.
The points which are uh, on the hyperplane, right, on the hyperplane with with alpha greater than 0, they also will have some alpha, right? So basically, if you think about this problem, initial problem, what does that mean? When you will be okay, and W star is equal to what? W star is equal to, this is the problem solution to this, right? Alpha xy alpha, right?
XY alpha.
Xy alpha. So which point should, what do you think, which point should contribute to W star? The points which are on the, or the points which are support vectors, plus,
Whichever positive alpha.
and plus the points which are misclassified, or plus the points which are classified correctly but not enough margin,
Not
right?
enough.
So
Yes.
all of
Correct.
these points should be contributing towards my W star.
W star.
Fine. So that means my W star will be able to accommodate all of this. Then it is possible, right? The correctly classified points we don't have to care about. That is the insight about from this. I hope it is understanding now. Correct? Any doubts here? Okay.
No, sir.
Okay. Fine. Okay. Now this is what we have seen from the perspective of what, alpha star and beta star. What is that alpha star and beta star? They are the dual solutions, right? Correct.
Yes, sir.
Now can we see it from the primal solutions perspective? Correct. So now these are the cases. Again, three cases will be there. What are those three cases? W star transpose xi yi if it is less than 1. What does that mean, less than 1? Correctly classified or incorrectly classified?
Incorrectly classified.
Correctly classified.
It's incorrectly classified, right?
Yeah.
Okay. Okay. So what are our constraints? Our constraints were like this, right? W star transpose xi yi plus epsilon I is, it should be greater than equal to 1, right?
Correct.
And that will translate to what? Epsilon I star should be
Then run to zero.
greater than equal to 1 minus W star transpose xi y. Is that fine? Hmm? Now the complementary slackness condition 2 says what? Or okay, what does that mean? Okay, if W star transpose xi y is less than 1, this is less than 1. What will happen then? Epsilon I star will be positive,
Yes, sir.
not equal to 0 also. It cannot be equal to 0, right?
Greater.
Positive.
It should be
More
positive.
than zero.
And if it is positive,
Yes.
what does that mean? Beta
Beta
star
is equal to zero.
should be 0. And if beta is 0, that means what about alpha I star?
Alpha star is C.
I'm just not putting it out the stars, but you understand that all of these stars, okay? Alpha
Alpha
is
star
Yes,
is
sir.
it will
C,
be C
right?
maximum.
So what does that mean? If the points are misclassified, these are the misclassified points, right?
The maximum, right?
They will contribute to my W star. Yes, right. This is what the understanding here. What is the next condition? It might be W star transpose xi yi. They are on the supporting hyperplanes, fine, or they are the support vectors. Let us say, or not support vectors as of now. Let us say they are on the
Not the
support.
supporting hyperplane.
What does it again? Epsilon I star is what? Is greater than or equal to 1 minus W star transpose xi yi. Is that right?
Correct.
And if I put 1 here, if I substitute 1 here,
Is zero. Zero.
so that means epsilon I star will become equal to,
Zero.
or not equal to, greater than or equal to 0. And if this is true, then what can I say about beta I star?
Zero.
No,
Oh,
it
sorry.
can be,
Epsilon I is greater than zero. Beta inside. Yeah.
beta I star can be between
Between 0 to C.
C. And if that is true, then what about alpha I star?
0 to C.
Is also between 0 to C.
Both
So
is
these are the points which are on the supporting.
Hyperplane.
Yeah, this are on the points on the supporting hyperplane, right? And that means they are paying the bribes, right? Or they are contributing to my not paying bribes. They are contributing to my W star, right? The primal solution. Okay.
Sir, if
What-
they are not paying any bribe, then why is that greater than equal to zero?
Uh, actually, see, it's not about the bribe thing. It's alpha star. Actually, what it is denoting is
No, no, I'm
W
saying
star.
about this sigma I greater than equal to zero.
What is
Sigma
it?
is this is eta or sigma, I don't know, but it's
Ah,
given greater than equal to zero. Yeah, yeah, this.
this point.
Yeah, yeah.
So then, what is next? This is
Yeah.
fine, huh?
No, no.
Huh?
Why is this greater than equal to zero? Since the bribe is zero, we're not paying any bribe, right? It's already correctly classified, or like it's on the supporting hyperplane.
Yeah, I think, see, that is fine, but mathematically we are looking at it, right? We're not looking. I understand what you're trying to say, but it is, uh, or can I say that, is it not possible that this point is on the other side of the supporting
Why
hyperplane,
it may be misclassified, though it is on the hyperplane.
right? And then it
Oh,
has to pay the bribe, right?
okay, okay, okay.
So
Because
this
it comes for the
includes,
misclassified points.
yeah. So I'm not saying
Yeah.
that, I'm not saying about only, I'm saying that they are on the hyperplanes. I'm not saying about whether they're correctly classified or misclassified, right?
Okay,
It
okay,
is
sir.
possible they are on the other side, like the case.
It is opera. It is like green
Yes,
is going to the red, but it is
yeah.
on the
Understood,
hyperplane.
understood, understood,
It is on the
understood.
Right.
hyperplane.
So this,
Yes,
it
yes.
has to pay some bribe, correct?
Correct, correct.
Yes, 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 correct.
And we are looking
Plus two
at this
drive or whatever.
point is according to, like, mathematically we are, like, looking at it actually, but that is fine. W star transpose xi yi is, so I should I write, or is it okay? Should I, this is understood, right? I have not
It's
explicitly written that, but
Yes.
uh, and another is greater than one. Greater than one means what? They are correctly classified, definitely, right? Okay.
Yes.
Okay. So now in that case also, what should I get it now? One minus W star transpose xi yi minus epsilon I is what, less than or less than zero?
greater
Uh,
than 0.
this is less than zero, right?
1 minus, yeah, less than 0.
Less
Okay.
than or equal to 0, sir.
No,
Less than
only
equal
less
to.
than zero, not equal to. Only less than
So
zero.
you have taken only
Greater
this
than,
one. Na?
right? Not
Okay.
Oh,
greater than equal to.
okay, okay.
Is it fine? Like,
Yeah, it's okay.
I think it is okay. It should be okay, right? So it is like, you see that here. Okay, I should not, maybe I'll write the same format we have seen it previously. I'm saying that epsilon I star is what is actually okay. I'll write down. It's like this, no? Or maybe
It's equal to 0.
okay. Actually, this thing is one minus W star transpose xi yi minus epsilon I is greater than or equal to zero. That was our actual condition, right?
Actual.
And then if I can say that epsilon I is greater than or equal to what, one minus W star transpose xi yi, right? And if W star transpose xi yi, if this is greater than one, what will happen? Epsilon I will go to the negative side, right? Basically, without explicitly writing that, we are saying that this condition is true for 1 minus W star transpose xi yi minus epsilon I is is less than 0. And what that translates to, what about alpha I star equal to 0?
Hmm.
Why?
Because the alpha star into, as per complementary slackness,
Yeah,
alpha star is this is equal to 0. Yeah.
right.
Correct.
So then this has to be satisfied,
0.
right? Complementary slackness 1. So this is from complementary slackness 1.
CS1.
Okay. And what is this? That means the points which are correctly classified,
Hmm.
they are not actually contributing to my W star. Is that okay?
Yes, sir.
Now that is clear, right? How we are actually using uh, dual solution and the primal solution. Is that fine now?
Yes, sir. Clear, sir.
Both way. You can
That,
interpret.
so that's it from this week. We may, or not this week, from the soft margin SVM. This is what you should know, understand how to classify these points. Okay.
Sir, how
Yes.
can we find the equation of the decision boundary?
Uh,
It was asked in a previous some question.
okay.
Just the points are given, so.
I need that question, right? How can I say directly to you that?
Come again. What is the question, Abra?
It's asking how to find, like, I'm asking how to find the equation of the decision boundary.
Decision
So
bound. You can calculate if this thing is there, that the data point is there. Na? Say x1 comma x2. You can calculate.
Few
Say
are
w
given.
naught plus w1 is equal to 0 or is equal to 1 if it's on the hyperplane. You take another one, say w3 x3 plus x4 is equal to minus 1. You can calculate. You can
W
calculate
is not
w naught
given.
and w1.
W is not given.
There was one hyperplane. There was an problem. I think in
Sir, if not
Reddit
given,
or
it is zero, no?
yeah. So you can calculate. Na?
If it is not given, it is zero, no?
No. It is say w. Say for example, something is on hyperplane. Say you w1, whatever point, say 3 comma 5, so 3 w's, so w 0 plus w1 is equal to 1, then
Shall
the
I
available
present?
time
I have the
absolutely
question.
okay, okay.
Yeah, please present that.
Yeah.
please present, then that will be good.
Yeah,
He's asking,
without question, I may not be able to answer that question.
I think he is asking for W
So
naught. If it is not
this
given, it
question.
is zero, no?
Yes, it is easiest.
This is easy, na?
Just put data point.
Yeah, 3 comma 4, 3
W
whatever.
transport x equal to -1. Just put -9 comma 4 and
4
second
as
equation
minus 1
3
and
comma
3
1
comma
put
4 as 1.
then
That's all.
calculate.
Get W naught and W 1.
And in this
Acha,
question, why
acha.
it is 3 comma 1?
Whatever, 3
Will it
comma
be?
1 or 3 comma 4
No,
doesn't
no.
matter.
I'm asking a doubt whether it should be 3 comma
These
1.
are the options.
Is it correct? 3 comma 1.
What is the equation
It
again?
is in this quadrant. No?
Maybe it is, maybe not rightly. It should be other way around.
These are the two
The
correct
point should be up.
options.
No, yeah, point should be up. It's 3 comma 1 maybe in the first quadrant. He's right.
Yeah.
He is slightly up.
Yeah. So
Anyway, that doesn't matter. You can easily get the equation of the hyperplane.
it's just like equation of a line, right? I think whatever it's contributing, I think that is what.
Oh, okay, okay, I get it. I get it. Okay, okay.
The simple straight line equation in coordinate geometry.
Yeah, that is what. Yeah,
Yes, yes, yes. My bad. Yeah.
but I think that point which is mentioned there, that is not correct one. Anyway,
Yeah,
but
maybe that
that is.
has to be slightly up.
But yeah, that's fine. Right. Okay. Till now, I think SVM things is clear. Let us try to understand what is bagging. Bagging also, I will not maybe explain it like all. The overall idea of bagging is what? To uh, to aggregate what? The weak learners, right? So actually, see, the scope of this course actually is not like covered very. I will not say that bagging is not the only method which we can actually use, but or not. It's not the only ensemble method, but we have only this method in our course, right? Which is
So why do you call these as an ensemble method?
ensemble is what, like you are aggregating.
Aggregating it. Okay, okay.
Yeah, so
That's
you can
sensible.
actually ensemble different weak learners. So it's not like
Mm-hmm.
only in this course we are seeing that random forest, which is actually the aggregating all the decision trees, right?
Mm-hmm.
But it is possible that you can take the decision one decision tree, one logistic regression possibly, or one some other uh, weak learner, right? And you can connect all and you can aggregate their results, right? So bagging is what it is called as. Bagging is called as bootstrap aggregate, right?
Aggregation.
Aggregation. And the technique we are actually using is the random forest technique. So what do you do in this case? You bag what?
With replacement.
Yeah, bags these entries. Yeah, so you first of all you have the data set, right? You have one single data set. We used to create different data sets from that uh, by using what, sampling. So in this case bootstrapping means what? It is sampling or uniform sampling with replacement, right? Since we may not have different data sets available, whatever the data set it's available to us, we are sampling it uniformly, right? And with the replacement, that is what you create different trees and you bag the decision trees. And generally overfit trees means what? You let them fully grown, right? So you will not uh, pre pruning. Have you learned about pre pruning and post pruning? Pre pruning means like you are not actually letting it fully grow, you are cutting at some level before it is completely grown. Fully grown means what? You will get all the labels, right? You try to uh, give the correct labels to each of the data points in the data set. Is that correct? That is when you get the grown decision trees. But generally those decision trees will be the overfit trees, right? If the outlier is present. Okay. And what about, this is the first step, and what is the second step?
Please say the statement again.
What is it?
Recently, you said
Your voice is too low. Can you just speak?
overfitting. What statement did you say?
Okay, okay. Overfitting. You wanted. Okay. So overfitting will okay. Let us say I will just draw decision boundary for decision tree, right? So how do you, let's say you have two features x1 and x2, right? Correct. And let us say your task is what to classify data points. And suppose this is one class, and this is your another class, right? And let us say the outlier is present here. Sorry, outlier is your outlier. Okay, is that okay? Is that correct? By looking at this data set, what do you think? What should be the correct classification we should do? So you should ask only one question, that you just draw this, right? So if your decision tree is like this, so you can say that if x is less than some maybe theta, right? If x is less than theta, what you should do? You should say, let's say, okay, green is what? Let's say what you should say, negative label or -1, and red is your positive label. So what I say, if this is true, right? If x1 is less than theta, what should I say? Say negative label, right? And if it is positive, or if it is greater than theta, what is that? If it is yes, and if it is no. In this case, what should I say? +1, right?
Yes, sir.
Okay. But now you wanted to classify this also, let's say. Then what do you do? You, I'll say that theta 1, this is theta 1. So now what you've done is, you should have actually stopped here, but instead of that, what you're doing here is, uh, you're saying that x2 is what, greater than theta 2. Let's say this is theta 2, and then if yes, I should say positive label, right? And otherwise negative. Is that okay? So what happened in this case now? If you look at this data, right? I think the first question, after the first question, if you have stopped, uh, that was the correct classification, right? Only
Yes.
because of this data point, which looks like to me as an outlier, what we have done is, we wanted to correctly classify that, and that's why we have asked one more question here. So think about this. Let's say you have different data set with different number of features, and you have asked questions still what? You ask questions still all the data points are correctly classified, right? This is what we have done here, right? We have asked the question still what? The data is correctly classified. If you have stopped it in the previous step itself, that means you were actually able to correctly classify most of the data points except this one, right? But now what we have done is, we have asked the question still, and this is what your full grown tree. In this case, what happens here? Overfitting. Is that correct? Because of this, now the overfitting happens. And and let us say, if suppose, okay, if suppose this new text point comes in here, what do you call this text point? What will be the label? Prediction. Now prediction will be this, right? But actually it should be green. So the test error will be higher, and the training error is going to be 0. Why training error is 0? because you have correctly classified all the data points using this decision tree. Is that okay? If you have any doubts, let's. Yeah.
Sir, should it be x2 less than theta 2, sir?
Less than theta 2 means this portion, right? This is on x2 is on the y-axis, right? X2 greater than theta means this one, and if it's correct, then we are saying that it is positive label. Positive means the red one, right?
Okay.
Am I correct?
Yes, sir.
But random forest weak
Huh?
learners. Which one?
Sorry?
Random forest use weak learners.
No, no, this is not random forest. No, this is the decision tree. I'm just saying that okay, we haven't reached to the random forest yet. So if I fully grow in this tree, right, decision tree, what will happen? Overfitting happens, right?
Yes.
Right.
Okay. Now what you do is you have, let's say you have the data set D
Slightly, can you go up because that? So rate is +1 or -1.
plus one. I just mentioned here, right?
So if x2 is less than x2 is greater than
Theta,
theta
this
2,
this
that
direction
means yeah. So that should be
plus one.
+1. That should be red. Okay, if it is -1, it is green.
Okay, I think I will just reverse the colors, right? Generally, you think the green color has positive and red is
No,
negative.
okay, it's okay. So you have written it here.
That's what. Okay. Now is it okay? So that means if I fully grown a decision tree, that might lead to what? Overfitting, right? Correct.
Yes, sir.
So let us say, and how does this the random forest works? So you have data points, the same data set you will be having x1, y1, x2, y2, and up to x and
X
y.
and Y.
What you do is you sample these data points into different data sets. So D1, D2. How many data points are there in this data set? Actual data set, and
And
in data points. You go from so you create the new data sets, let's say k data sets from this original data set. And how you do it?
Usually this k is root over n or what?
K is what?
Root over n.
This
The
k
number of you take up to say k is root n times bags.
number of bags you're talking.
For example, 100 data points are there. You take 10 bags. Root over 100 is 10. Usually that's the empirical formula used. Say
I
for
don't know. Like it's not actually
I
required,
think it is
but
mentioned
it is,
somewhere. It is root over
yeah,
of
root or D actually it is mentioned.
yeah,
So
root over d.
so
Then 100 data
D
points are there. You take 10.
D is not the data point, right? D is the features, right? Number of features.
So you take only root over. You take only 10 features. If it 100 features are there.
So it depends on the features. Let's say okay, each xi is, let's say if it is 100, then only you can take root of D. It's not number of data
Okay.
points. It's root
Okay. Okay. It's a number of root over a number of features.
features. Yeah, that is what I'm trying to say.
Okay.
So okay, that is like okay. These are the conventions and all. It is not necessary that you should follow that only, but it's like the people have found out better results for that. That is what it is there. But that generally doesn't affect it. So each of this data set we should have how many data points? D1 should also contain n data points. D2 should also contain n data points. D3 also n, and all k should have n data points. Fine. But how should we bag these data points? Right. So or how that data set all are fine, all are n data points, but they all should be sampled with
Replacement.
replacement. So in that case, what will happen is we can get the repeated data points into one bag or in one data set, right? And that also might lead to overfitting. That is also possible, right?
But the only advantage is that you are
By
killing the correlation.
not overfitting, basically, it will introduce a bias.
But
Uh,
it will reduce your correlation.
Correlation, yes. So that is fine. So what you do is in on each of these data set, you apply weak learner. Weak learner in our case is what? Decision trees, right? In random forest, to do decision trees. Fine. So is that okay? And what you do is whatever, and you should use the full grown decision trees. And let's say they give you this h1, h2, h3, let's say like that, so hk, fine. And you do one thing, you should find like last answer, right? It has to be the sign of 1 upon, let's say, k 1 to a hi. Is that okay? What is hi and h1, h2, h3 here?
The hidden H is for hidden, no sir.
H is for
So the
Hidden.
H is the prediction, right?
H is the
Prediction of that particular tree.
okay, something happened. Okay, H is the prediction, yes, for a particular decision tree. So okay, how this will work, right? That is the question. So what you do is you have one test data point. So this is what you have done, right? So you have done the decision tree. Is that okay? You have found out the data points. Can I take a small example, like small data points? Suppose
Yes.
x1 y1, x2 y2, and let's say up to x4 or x5 y5. Okay, this is your original data set. Let us say now what you do is d1 will be so I'll just write down the back. Suppose it can be, can I say just only x1 here and x2 here and x5 here? But what that means, it's entire pair. Okay. Okay. So what you do is you just pick x1, x2, x3, x1, x1. This is one back. D2 is, let's say, x1, x2, x3, x4, and x5. D3 is, let's say, mm, this bag is, suppose, x1, x2, x3, x3, x2, right? Okay. Now I have developed a decision tree from here. Let's say decision tree one. And now what I feed is, this is what training happened, right? Till now the training has happened. Now I feed x test here, one data point here. Okay. And whatever the output it is showing to me, that is my h1. Now we have on this data set 2, again I have applied a full grown decision tree, that is training happened there. And now I have used x test here, or to find out the prediction, and the prediction for x test is h2. That might be equal to this one, or that might be different. Understand? And now this is decision tree 3, and now I fed one another data point, which is x test, and that prediction is, let's say, h3. So suppose this h1 is 1 or plus 1, h2 is, let's say, minus 1, and h3 is, let's say, plus 1. Fine. This is the prediction for what? The test, same test data point. Okay. So what will be the final prediction? That is equal to sine of plus 1 minus 1 plus 1
by 3.
by 3. That is sine of what is it, plus 1 by 3. And what is the sign of this?
Positive.
And that will give me, that is my final prediction there. Is it okay? That's how you find out the uh, decision. Now you understand it?
But sir, for this type of questions, we have to make a full grown decision tree for each of the data set.
No, no. So in the in the question paper, it will not be like that, right?
So like for this bagging, like what can we expect? Like what type of questions? Like some
So
idea.
you may be able to, like, it is given to you that this is the, this is what, maybe what, it is possible that you may get that decisions already given to you and asked you to find out this what will be the aggregation, right? That might be one possibility. The chances that you have given the data sets, and maybe you have given some decision trees, right? And then you will have to find out the for one next test set. So decision trees will be given to you already, let us say. Okay.
Okay,
And
decision trees will be given, and for the test point, we just have to find out the labels for each of the decision.
labels, and then you have to aggregate that kind of also questions, you can find it out.
Okay. Okay.
Okay. It will not be very hard questions. Okay. So now the next technique is what?
There
Boosting.
is
And
one
in that
question.
boosting, huh?
So one question from the random forest.
I
The-
Your voice. Can you just type your? Uh, can you just type it here? Maybe I don't know.
I'm not audible, sir.
Yes, now you are, but
So actually, there is a statement in the grade assignment
uh,
like generally weak learners in the random forest tend to overfit. What does this mean, sir?
yeah. So that is what I showed to you, right? So if I fully weak learner, dysentery is weak learner, right?
Yeah,
And if I
yeah.
use the full grown dysentery, they will tend to overfit, right? Because they will try to accommodate these outliers.
So, but if it is weak learners, then how it can overfit? Weak learner generally underfit
Why?
because in weak learners we generally
Weak learner mean what? They will actually do what? Weak learners is not like, uh, okay. When is overfitting occurs? Can you tell me when?
when we go full depth or when our decision tree is purely pure.
No, no, no. In general, like, what does that mean? Like, in terms of testing error and train error. So during training, the error will be very less, right? If you think about this problem, what is the train error here for this decision
Zero.
tree? Zero,
Zero.
right? But let us say any text data point will come in. If it is this test data point, what it will, let's say this is the test data point. Uh, what will be the error? High, like it will be higher error, right? So it's not. So that means when the test error is high and your train error is low, right? In that case, we call it as
Fourth.
what, the
High.
overfitting. And now, can you tell me, is it happening in this case? Yes, right.
Yes.
That's why they are weak learners, and weak learners are generally tend to overfit. They don't
Sir,
go.
weak learners means that like they learn slowly, right? So after n number of iterations, it will overfit because for every iteration it's going and fitting, going and fitting. So it happens like this, right?
It's okay. Weak learner is basically, it's not like,
So weak learners can be overfit and can be underfit.
yeah, yeah.
Both
So
can be.
yeah, weak learner means like you are, they are not actually giving you the proper results, kind of like that, right? Like, uh, because their tendency to, if you try to full grow it, like now let us say if I use a random forest, will that be a strong learner compared to the decision tree?
Yeah.
Yes, it will be stronger.
So that is what, like, strong learner means what, it should not be overfit as well as it should not be underfit also. So it's kind of an optimal learner, right? That is what strong learner is, right? Is that okay?
Sir,
Weak learner,
sir,
yes, yes.
for weak learner, will the training error be less or large, sir?
Yeah, see, weak learner means it's not actually good one, right? You think of that perspective. So weak learner is that learner, it is actually not doing it well on your data set, right? And that is possible when on both the cases, right? Overfitting, do you like overfitting or do you like underfitting? You don't like both, right? You don't want the data should like it should be underfit also, and you don't like it to be overfit also. We wanted that sweet spot, right? Which is the optimal learner. So the optimal learner is actually, you can think of as strong learner. Apart from that, anything is there, it's weak learner. So dysentery, right?
Uh,
Generally they try to overfit, and they are weak
I
learner.
got that. I get that point. I'm asking whether the training error will be less or more for
Okay,
weak learner case.
okay. Okay. Maybe I'll draw one diagram. Yeah, I understand. I
So
understand.
if it is underfitting, then training error will be
Yes,
zero and
not
test
zero actually. It's low. Okay, I'll draw one diagram. You maybe try to understand that. So this diagram is based on, let's say, it can be, I can actually draw it for two things. Let's say for number of iterations, hmm? Or and on y-axis it is, let's say, error. Okay. Now, if you learn anything, right? If you train the model for longer time, what will happen? The error will reduce, right?
Yes, sir.
Just try to do this. Oh, PDF is not working. We just give me a minute. I think I should close this one to open the other one. It's not working properly. Okay. I'll draw a diagram which is error versus, let's say, number of iterations. Okay. Now, if you train a model on a same data set for longer time, what will happen? The training error. This is training error, right? It will try to reduce, right? That's correct.
Yes, sir.
But what will happen to the test error? It will reduce it first, right? As you train more, but then afterwards, what will happen? If you try to train it more and more, right? That means you are trying to fit the uh, outliers, and in that case, what happens? The test error will, typically it will go high, right? So this is my test error. My test error, right? Now, this case here, it is called as overfitting, or in other words, this is the case of high variance. And what happens here, if you don't train properly, right? What will happen? The training error and the test error both are high, right? So this case it is of underfitting, and that is also a case of high bias and low variance. High bias, low variance. I'm not writing low variance here, and here I should write low bias. So I don't want this to both the conditions, right? Similarly, right? So this is what I have shown it for number of iteration. The same diagram I can show it for number of samples in a data set. Or so let us say if you have less number of data points to train on, what will happen in that case? You will have higher training error, right? But as you increase the number of samples, what will happen? Your training error will reduce. And what will happen in your test error? If your data set is having less samples, your test error also will be high. Then as you increase the number of samples, your test error will go less, and again it will go high, right? Because if you have like very large data, then what will happen? You will try to overfit again in that case. So this is your test error, and this again underfitting, overfitting. This is overfitting.
So what is the difference between the earlier graph and this one?
Same difference. The only thing is, I have shown it. So your x-axis is number of iterations. So this is
Number
for
of iterations.
fixed data set, right?
We
So
fixed data set.
fixed
Okay.
data set. If you train longer, this will happen, and this is for number of samples, right? So you have different data sets. If your number of samples are increasing, so let's say you have only one data point to uh, train on, what will happen? Training error also will high, and the test error also will high, right?
Also high, right?
Right. And if you have very high number of data sets, right? Like in case of KNN, let's say, that also will be the issue, right? If you have number of samples larger. So these two cases are there, and you will have to understand. This is actually, see, this is plotted uh, by
Number of
like,
iterations.
yeah. So number of iterations or number of samples, and this is like a practical graph. It's not like it's not like the theoretical one. So people have done the experimentations, and based on those experimentations, this is what found out. I hope it is clear. Okay. Now we
Yes,
have
sir.
done with the tagging. Let us start with boosting. I'll, you may actually encounter the numerical questions from this uh, boosting algorithm. So understand the algorithm properly. In that case, we have seen the AdaBoost. AdaBoost, right? Mm,
AdaBoost means what? Adaptive boosting.
yeah, adaptive boosting, right? So the adaptive means what? You are actually learning it while iterating, right? So each step or each iteration you go, you will uh, learn the weights, right? You're changing your weights accordingly. That is what it's adaptive boosting. So in this case, we use decision stumps, right? What is decision stump? It is the shortest decision tree, right?
Just one question.
Hmm. Yeah, go ahead.
No, sir. The meaning of decision terms, like just one question.
Okay. I thought you were saying this one question. So yeah, it can be a one particular question, or maybe the two questions or two layers, as you say. Fine. So in this case, okay, the algorithm is this one. I'll write down the algorithm. So let's say you have the data set x1 y1, and you have n number of samples. Okay, each of xi is in RD, and each of yi is actually in between, belongs to +1 and minus 1, right? Okay. Now what you do is you do uh, you what you initialize with, you actually provide weights to each of these weak learners, right? This is also weak learner, right?
Yes, sir.
Decision stump. So I think someone has asked me the question before. So decision tree also is a weak learner, and decision stump, decision stump is also a weak learner.
So
So which
only thing is it is not full grown tree. Maybe can I say like can we say
It is like a very short tree, like
a
the
short
shortest
tree?
one.
It's not a full grown tree.
Yeah. So short tree, what is the problem? It's a problem
It
of
will not overfit.
high bias, right? Underfitting.
It will not overfit.
Yeah. So it is underfitting. It will have
Under
high bias,
Yeah.
right? And full grown tree is overfitting.
overfitting.
That is high variance and low bias. Is that okay? Now the
Yes.
and
Right.
both of them are the weak learners.
Weak.
So you take all of these weak learners and you try to get a strong learner out of it. That is what actually it is, right? So now it is like initialize your weights, and we use the uniform initializations of the weights to, right, and that is what, like, you have n data points, you give uh, 1 by n, right? So that weight to each of the data point initially. Now what you do, now you try to iterate. So iterations will be 1 to t, let's say t iterations. What do you do then? What is ht here? Ht is the output of a weak learner. Hmm? Fine. So you, and for that what you input? The data set. Data set is written by here, like by, or denoted by s here. So s, and what you do here, dt. Dt is what? Weight. Hmm? This is my output, the output of the weak learner, which is a decision stump in this case. And st and that input is your entire data set along with the weightages. Now what you do is, based on the outputs, right, you will know that how many data points you have misclassified, or whatever the errors are you're obtaining, right? On that basis you change the weight in the next iteration. T plus 1th iteration, you change the weight for each of the data point, like how, based on this formula, which is called as, the dt is what, the weight in the previous iteration for the data point, into e to the power alpha t, and dt for the data point in the previous iteration, e to the power minus alpha t. And when it is plus alpha t, if it
Wrongly
is,
classified.
yeah, so h wrongly classified in the tth step,
Okay.
tth step, right? Okay. And if it is correctly classified in the tth step, you actually reduce the weightage here, correct? You reduce the weight for correctly classified one, and you increase the weight for the incorrectly classified. And how can I say increase and decrease? Because e to the power minus alpha will be lesser than e to the power plus alpha, right?
Can you take slightly up the
Yeah,
initialization?
yeah,
Initialization is always 1 by n. Huh?
yeah. For, yeah, it's uniform initialization.
Okay.
So uniform weights given to you. Let's say if you have 5 data points in a data set,
So
what
1
will
by
be
5.
the 1 by 5? Yeah. And what is the next step? Next step is normalize all of these weights, right? So yeah, so this d, this is what tilde, right? So this is what each data point, and you normalize for each data point. This, like how you take this weight, which is we have done it here, and you sum it over. Let's say I equal to 1 to n. Is that okay?
Typically, in some of the question, it is not said you should normalize,
Yeah, that is
but
okay.
if it is not mentioned, you should normalize. No?
Yeah, if it is not mentioned, you should normalize it. Okay.
Sir, does AdaBoost overfit if we keep adding weak learners?
No, it will not actually, right? It's not like you are adding it. You are actually taking the weak learner, which is the distance term. For example, you're saying that, okay, so for example, you have data points like this: 1 plus 1, then 1 minus, okay, not 1. Can you just give me some toy data set here? Let's say 2 plus 1, then let's say 3 minus 1, and minus 1 minus 1, so minus 2 minus 2. Is that okay?
Yes, sir.
Now let's say my decision stump is like this. So this is x, right?
Yeah.
This is x1, x2, x, not x1, x2. Actually, you are understanding that x is a feature, right?
Yes, sir.
Let's say x is entire feature, and these are the data points from that feature. If I say, if x is less than, or x, okay, x is greater than 0. So my question is, x is greater than 0. What I do is, If it is yes, then I label it as +1, and if it is less than 1, so it is no, this -1. This is my decision step, right?
Yes, sir.
Decision tree or decision DS is decision step, let's say. Okay, right? Only one question I have asked. If x is greater than 0, I should say +1, and otherwise I should say -1. So what is HT here? uh, okay, what is, first of all, what is the error here? What is the misclassification error? So first data point will be classified correctly or wrongly? Correctly.
Correctly.
Correct.
Second data point.
Correct.
Correct.
Third data point.
Correct.
Incorrect,
Yeah, yeah,
Incorrect.
yeah.
That will be incorrect.
because actually it's -1 and it is +1, right? Now here it is -1. This is correct, right?
Correct.
This is
Correct.
correct.
Only
So
1 out of 5
1 out of 5, right?
is the error.
This is the error. Now I should actually find out alpha. Let's say, I don't know. So first of all, this is called as epsilon, right? Alpha actually you can find out using this is 1 of 1 minus epsilon of 1, right? This is what. And what were the weights initially for each of the data points? 1 by 5. Okay.
1 by 5.
So for first data point, what will be the weight in the t plus 1 step? So let's say d1 is equal to 1 by 5 into e to the power minus.
Minus alpha. Minus alpha.
uh, can we just, for simplicity, I will not use this complicated expression right now. Is that okay? I'll just say that this alpha is this one, 1 by 5. Is that okay? Hmm?
Yes.
Actually, you should do that calculation, but I'm currently I will not doing. I'm not doing it. I'm just going with this. Let's say minus 1 by 5, and uh, right. This is okay. What will be
Okay.
the weight for D2? 1 by 5 e to the power.
Minus 1 by 5.
For D3,
Plus 1 by 5.
1 by 5. D4
Minus 1 by 5. And
and
minus 1 by 5.
D5. Is that okay? So you have actually given this equation the more weightage, and this another as less weightage. What you do is then you just multiply it with this d1 with respect to its corresponding h1. So what is the output of this? D1 into what is correctly classified, right? H1 of x is, was it correctly classified? Yes, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
I should say +1 plus d2 into +1 plus d3 into,
Minus.
no, +1.
Uh,
Okay, +1. Then d4 into -1 and d5 into -1. So if I average it out, or if I take it like, I think this and this will get cancelled, right? Because they are saved. Correct, right?
Why
So
D3 is plus?
because we are taking, okay, so the final so AdaBoost, how it will actually, a star final solution is actually, this is a star is equal to sine of summation of I equal to 1 to n alpha t ht of x. Ht of x is what? The output, right, at t step.
Correct.
Hmm?
That's correct.
So what was the output? So okay, I'll write ht here. Ht was
Plus. First
plus
is
1,
plus, plus,
plus 1, minus 1, plus 1, I'm
plus
sorry,
1.
plus
Okay.
1, minus 1, and minus 1. Now I'm using all of these STs here.
Okay.
That's why it is positive. Now I should take, so then it will be sine of that, right? All right. So now sine of D3 is like, it's a positive weight, right? Positive weight, correct? So now it will give me,
So actually, you're taking the
sorry,
predicted label or the actual labels here. For D3, are you taking the predicted label or the actual label?
predicted. We can't take actual now, right? We are learning, so we should take positive label only.
Okay.
So now, and then again, if you see that again, in the next iteration, what will happen with this? You just again calculate, and it will go over and over. right? So next, in that next iteration, again you will see that whether error is 0. And when should you stop?
When you get the same answer.
So basically your training error will become 0. So that means it will be able to classify it correctly, classify the data points correctly. So the question here is whether it is going to overfit or not, right? Or this is going to be overfit or not.
Just a stump, right? So now we change the
Yes. Yes.
weightages.
Yeah. So it is the same stump. We're just actually changing the weightages. And when I put it
Wait,
this,
this weightage is used to compute the output, is it?
yes, output for what? But X test, right?
Yeah.
And now, see, then it will actually see it will be useful. Okay.
The weightage I thought was supposed to a probability based on which you are selecting those samples, right? Actually, that is supposed to be.
And that is what is happening, right? I'm not so in this final prediction. This is not this. These are going to cancel, right? So as my if I just go ahead and ahead, right? So if they are correctly classifying, this weightages are going to get 0, right? It will go to it will tend to 0 for correct classification. Only it will have penalty for the
This is the postmortem that we are doing in a paper. Now in the system,
ah,
whatever the stump that we are given,
hmm.
it remains the same. Is there a how do I put this input to the system?
uh,
See, we
okay, yeah. You go ahead again. You just
slightly,
explain it properly. Yeah.
roll it up a little bit so that I can
Hmm.
probably talk. Yeah. Okay. Now there is a question asked whether x is greater than 0. Correct? No, no.
There is
This
this
is
one.
already fine.
What you are talking about?
After this,
Ah.
when we come to the decision stump,
Hmm.
there is a question which is x is greater than 0. Based on that, where there is a classification done.
Hmm. Hmm.
The quality of classification is being analyzed here.
Okay. Yeah. Right.
Now we derive some results.
Hmm.
How do I implement it in the system?
System, you means to say like any new variable comes in and in that point, right? You're just talking about that. Uh,
As of now, it has some error.
hmm.
Correct?
Yeah.
Now, based on the analysis, it is supposed to take the feedback and then modify itself.
Correct. But what are you modifying here?
Yeah, that's what I'm asking.
The
What
weightages.
I'm modifying so that I have a stump which correctly identifies. You get my point? All I ask, I mean, finally, I need a system, a
Hmm.
model,
Hmm.
which without me going and computing something should be able to tell me correctly whether this
Yes.
data is
Yes.
plus or minus.
Right. Right. Yes.
Right?
Yes.
Now, based on this 5,
Hmm.
I am trying to train this box. X
Hmm.
is greater than 0, is less than 1, whatever it is.
Hmm.
Now, I should be tweaking something here so that it modifies and correctly tells me. That is what I would call that as an ADA. This is an ADA, right?
Yes. Adaptive grid. Yes.
ADA.
Yes.
So, how does it get that adoption? What we are now doing is we are computing something to figure out what should be the weightage.
Yes. For each of the data point.
We
How
got the
much?
weightage. Now,
Yes.
initially we started everybody 1/5
What is adapting here? Weightages only.
weightages. Now,
Yes.
where do I implement the weightages?
So yeah, so when the okay, I understand that. So when you get like the final weightages, right? Let's say you trained it,
Yeah.
and you will get, let's say this is the final thing, right?
Okay.
For weightages. So now these are the weightages corresponding to those data points, correct? Is that fine?
Yeah.
So now okay, any test data point comes in. What do you do then? So you have
Wait, these weightages are for the training data sets.
huh. So we don't have any weightages for the test data set. That is correct. So,
So
but this weightages will ensure me, right? Okay.
where do I incorporate into the system?
Yeah. So you are saying that if I have any test data point, right? What
Yeah,
should I do with that? That is what your question is, right?
correct, correct.
Correct. So, okay. I think it was anyway. That is not mentioned in the lectures,
I
but
know it's not
I,
covered.
yeah, it's okay. I'll tell you about that also, like how this will help me, right? So, the final goal is to what? Uh, uh, how should be I able to test error, right? Or uh,
I want a modified stump with
actually, you are not modifying the stump, right?
then
You are just modifying the weightage according to the stump. So stump will be the same, even if my
okay.
test data point will come in. But what that will do is, based on the, let's say if you have any test data point here, right? If so, x is greater than 0. Let us say, actually we are actually looking in this example, particular example, we are looking at only
Let's take, no, no. Let
one
us see whether
feature.
the training comes to zero.
Yeah, training will be 0. Yes.
How
Huh?
one no one, which was getting misclassified.
So
Three
what?
minus one.
Yeah. So now what will happen is these weightages, right? They
Hmm.
will go 0, 0, 0 at the end, right? Sorry, classified will go 0, and only train will have the higher weightages, right? And at one point, it will happen that it will have the higher penalty to that. Is that correct? So that
No.
means eventually it will be able to
I
correct
will leave it. I
further.
will leave it. Let's leave it. Maybe after the exam we will discuss.
Okay.
Let's not bother about it. It's not in the portion. Why waste time?
Okay.
Leave
Fine.
it.
Yeah. So okay. Anyway, I think the last topic it is
We will discuss after the cases.
fine, fine. We can discuss about it.
I,
Anyway, that is not like very. I would say very in the deep manner. It is not discussed
no,
in.
no, but it's okay. It can wait
Yeah.
48 hours.
Right. So yeah. So now the
What's the
neural networks.
answer? What is the answer for the? What is the solution
Sorry.
for the question?
Okay, there is no like final solution to this right now. This is like how we. This is the gradient like boosting algorithm, right? So this is how you just. So this is the algorithm, like fixed algorithm. Based on that, what you do, you just try to find out weightages, let's say, right? Weightages, and finally you aggregate them. So okay, and okay, I think I should finish this algorithm with here. Let us say your final h star of x will be what? It will be the sine of. Okay, I think I got it, but yeah, let's discuss it that later. It's 2 of x. Fine. This is okay. And this is your final algorithm where I should say that alpha is actually, and what is epsilon here? Epsilon here is the number of misclassifications, right? Or I should say misclassification error. Misclassification error. And in that small example, I took the that means out of the 5 samples, right? One was misclassified. Was it correct? So the mixed classification error was 1/5, and alpha is a function of this epsilon, that which is the misclassification error, that is half ln of I think 1 minus
1 minus E by E.
yeah, that is it, right? And yeah, I think you can use it here, and you can not use normalized weights, and you just find out later on uh, the final hypothesis for this, right? So okay. Uh, Fine. And what is the last topic which we have to see is neural network, right? So I will see based on the like whatever the examination point of view, we just see the simple. I think it was very simple neural network we have studied here. What was that? Let us say you have x1, x2, x3. These are what input data points, right? Their input. I don't know how many input here it has taken, but okay. In general, any neural network will have uh, 3 types of layers. One is what input layer. Another is hidden layer. So hidden layer can be like it can be layer or layers. It can be multiple layers. And what next is
Output.
output layer. Okay. So basically, input layer and output layer will be basically one, and hidden layers can vary, right? and each of the hidden layers actually consist of neurons. So let's say if you have three inputs, hidden layers may have, let's say here, let's say if you have two hidden layers here, let's say hidden layers, okay, and then you will have what, uh, output layer. So output layer can have one or two, but for our simplicity, like here whatever you are discussing, right, you might have only one output uh, layer, right, or output neuron, we'll say. There is only one neuron in the output layer. So what is it, okay, this might have, okay, I don't know, it's not like very explicitly mentioned everywhere in the lectures, but this will have two functions, right? One is pre-activation function and the activation function. So whatever this portion is there, it is called pre-activation, and on the right side it is called the activation function. What does that mean? We'll see that. uh, do we have included biases into this? No, right? I don't know. Okay, let me think about it.
No,
So
bias, we are not including bias. Generally, they avoid it. That's
okay, so what is this? uh, let's say you have, uh, I wanted to say that it is w1 x1, right? And let's say w11 x1, let's say here I say w, this is w2 1. So this is what, I'll say that, okay, maybe w11, so, or ij, j and I. General terms I will try to write down. W, this is J, and this is I. So I is for the hidden layer, right? So I equal to 1 means what? The first hidden layer, right? I equals to 2 means the second hidden layer. And J here is neuron in the previous uh, previous layer, let's say. Previous layer. Okay. So this is W11 means what? It is a weight coming from the first input, let's say first neuron in the input layer, to the first uh, first hidden layer, or first unit of the hidden layer, let's say in this case. I don't know what notation sir has used. Is this I don't know, maybe I should use a consistent ones. Yeah. Sample. Okay, I'll come to that. Before that, I'll try to explain this one. W21 is, let's say, from this, and let's say this is W31. So in this case, what will be my pre-activation for neuron 1 in the hidden layer 1? That will be, let's say I'll denote it by Aij as, in this case it is A11. This is what, it will be W11 of x1 plus W21 of x2 plus W31 of x3. Is that okay? Similarly, I uh, can have this from here, from here, right? Uh, maybe I'll do one thing. I'll just read for the first, then blue from the second. These are the weights, right? Okay, so this is not wrong. This is wrong. This. Is that okay? So this is how you can actually calculate. So whatever the weights into this, that is what your pre-activation. This is the pre-activation, and what will be the activation? So activation can be denoted by Hij, and that can be, let's say if I use the sigmoid here, right? sigmoid function over here. So that will be just sigmoid over aij. And how does that will look like? What is the sigmoid function? It's 1 plus 1, 1 divided by 1 plus e to the power minus aij. And aij in this case will be this entire thing, right? And similarly, you can actually connect it to the next one. But now we'll just take the simple case here, which is of this one. Let's can I just show you the simple neural network? Because anyway, the neural network, all of that you will study into deep
Can
learning
you go
software.
slightly up?
No,
Slightly up.
I'll draw one more diagram, the simpler one, and we can discuss it. Is that okay? So the weights will be very clear. I'll just make it half here so that I can just show you the pre-activation. Let's say this is x1 and x2, only two uh, features here, right? Two features. This is one hidden layer, the W11. This W11. This is W12. And it's going to be your, this is what? W21, your W, and that is your, this is your pre-activation. This is your activation, let's say. And what you do is the next set, this, so it is, let's say, W uh, 1 to, I can say, 2. This is your W2. This is this side H1, this H2. This I can say that A11, A12. Yeah. Now, is it okay? This is your output layer. This prediction. This is why I said. Okay. Now, what is the doubt? Can you tell me? Or do you want me to go up? You can tell me that also is fine. This will be out, right? So suppose I have used. Am I audible?
Yes, sir.
So suppose I have used the sigmoid function here, sigmoid function, and let's say softmax here. Softmax is covered, right? In this, because I don't know, I don't remember it, but is it covered softmax to calculate the probabilities? Or ReLU is covered. ReLU is covered.
Relu is yes, covered.
So what is used for output layer? ReLU or sigmoid? Okay, okay, fine. I'll just, I don't know if it's softmax is generally used for classification purposes, but I think it is not covered in the lectures. Sigmoid function is what? Sigmoid is basically it is denoted by sigma. So sigma of x is 1 upon 1 plus e to the power minus w transpose x. Right? Let's say if it is a vector, and ReLU is uh, basically, let's say, r of x, right? It is what? I think max of 0 and,
Sign of
so what is it?
Sir, when do we use which activation function?
No, that is given to you generally. So generally, see, softmax, right? Softmax, it is not like hard and fast rule that we should use it, but it is based on what type of output you want. Let's say your output, your purpose is to find out what the classification, right? So if you wanted to use this for classification purpose, then what do you want? Like your probability should be between what, 0 to 1, right?
Yes.
So sigmoid is better for that, right? Because sigmoid always gives you the probabilities between 0 to 1. In that case, actually, softmax also is used, but I think softmax is out of syllabus for MLT. You will encounter into this deep learning later. But softmax
And
is majorly. And for, let's say, your regression is the your output is regression, right? In that case, ReLU is better. Why? Because it is based on that, right? So it is okay. I think I've just written x, but let's say between 0 and W transpose X, right? What does it mean? If you are if it is positive, right, so then that will take and that means it can take any number, right? It is not
Yes.
clamped between 0 and 1. So that is what so that's how you use it. So generally ReLU you can use for regression type of problems. Sigmoid or softmax you can use for classification type of problems. In between, majorly, right, majorly most of the deep learning architectures, right, they use sigmoid because it actually is in between 0 and 1, so that will be good. And it is not needed that you should use that many number of neurons. You can vary the number of neurons also, but that is okay. But that is not the scope of this. This is like very introductory lecture for neural networks. It's not like anything covered in that, but it is there in our syllabus. That's why we need to learn it. That's it. Okay, so what do you do in the pre-activation layer? What do you do in pre-activation layer? How do you compute the pre-activations? Let's say A11 is my pre-activation. What is how does it will look like? A11 is W11 of x1 plus W1. Okay, I think it is 21, right? W21 of x2, right? And H1 will be what? Let's say if I use sigmoid here, then H1 will be 1 upon 1 plus e to the power minus A11. Okay, A12 is W W it's 1 2 2 W12, it is x1 plus W22 of x2, that is A12, and h2 will be what? 1 upon 1 plus e to the power minus 8. Is that okay?
Yes, sir.
Okay, so you can actually write these two things into the vector format also, matrix format also, right? So how will you write A11 in matrix format? It will be W11, then W, I think, okay, I think it is not matrix, but yeah, vector format, let's say. This W1 transpose, okay, this W11 is W21 of x1 x2. Is that okay? This is what A11 is, and A22 is, or A12 is this W11, no,
Sir, two.
W12 and W22 of x1 x2, and I can actually write activations like this. So A11 and A122 is equal to W11, W1, W21, W12, W22 of x1 x2. Is that okay? So this way the calculations will be easier. This is A11 and A12. Then we have calculated H1 and H2 here. What will be your output? The prediction. So prediction, at let's say I have used for prediction. Let's say I have used ReLU function. So in that also you can actually make it as two. One is pre-activation and another is activation. Now, can you tell me how does it will look like? So this will be okay. From here, if I say that W12 of H1, right? So it will be W12 of H1 and W2 of 2. Or let's say I'll not write 2 here. I'll just say output. O. So W10, W2O, H2, and this will be my pre-activation set. So this is W2 not H2. Is that okay? This is, let's say, pre-activation for output layer. And what will be my prediction then? Last, the prediction is max of
0 A 0.
Yeah, so I think max of uh, between 0
A.
and right? Is that okay? That's how, if it is a regression problem, if it is, let's say, a sigmoid problem, let's say if I use sigmoid, how does it will look like? So y hat will be what? Y hat will be 1 upon,
1 upon 1 plus p power minus a naught.
right? Is okay. But let's say these are all weights, right? These are all weights inside here. We need to learn those weights, right? That is what our, actually, for classification also we have done that, for regression also we have done that. So we use the squared error loss here to, let's say, for regression, right, to learn weights, and we try to minimize that error. In this case we use what, cross entropy loss to learn the weights. So there is actually a back propagation method. It is not, I think, in the scope of our syllabus here, but cross entropy loss is what, is y hat minus y hat, or sorry, not minus y, minus y log of y hat, right? This is what cross entropy loss is there. What is y here? Y is the true label, and y hat is what, the predicted. I guess it is okay.
What is that minus y into log p minus 1 minus y into log 1 minus p? That
That
is
is
not
also
possible.
cross. No, that is also. So basically, that was what, like, if I write down that, it is minus y log of y hat, and I think it is minus, I
1
think,
minus y
y log
into
of
log 1 minus y hat.
1
1
minus y
minus
hat,
y.
let's say. Yeah. Okay. So in this case, what will be, let's say, for classification purpose, right? Your labels will be what,
0 1.
0 1, right? So if I have y equal to 1, what will be the cross entropy loss? It is minus y log of y hat, right? For when
Correct.
y equal to 1, and if y equal to 0, then cross entropy loss is okay, not 0
No, no, no.
exactly, that
Y
will be
0 is
this one, right?
yeah, log of, yeah, minus log of 1 minus y.
Minus, yeah, so log of 1 minus y hat, right? I think I have done it wrongly here. It is log of y
Yeah,
hat, right? So if this is what the condition is, right? When y equal to 1, this is minus log of y hat. When y equal to
correct.
0, this is
Log
minus.
of 1 minus y hat.
So if you can just put it here, so if you just have 1 here, then it will be minus log of y hat, that is for 1, and if it is 0, that's going to be 0, right? Okay, I think I shouldn't, this is
Sir, we will have summation, no, sir, there in that formula. Summation of
where
I is equal to 1c.
I is equal to, where
Here. Minus y log y hat.
huh?
Here we will have a summation uh, I is equal to 1c. This
C, C is what, C is what, C is number of classes, huh? You're
yeah.
saying about C of number of classes. Yeah, so that is when, that is possible when you have like, I think, more, like, let's say you have more than two classes, right? So if you have more than two classes, then each of that you will have separate thing, right? But let us say if you have only two classes, so then either you will predict as one, or you predict as zero, right?
Okay.
Yeah, okay, I think I'll get that. So when, so the prediction also, right, that y hat, if I use the ReLU activation, so okay, this cross entropy loss is, I think, particularly only for ReLU activation. What will be that, ReLU or sigmoid? Okay, let's say if it is ReLU, right? Then I think it should be okay. Okay, then fine. Okay, I think we should, I should go for the generalized case. But this is okay. This is also fine. This will not give you the bad thing, especially your y hat is either 0 or 1, right? The prediction is either 0 or 1, but the general is this one.
Cross entropy, you
In
don't.
general, yeah,
Cross,
generally I think we have used this cross entropy in the decision trees, right?
no, that's not cross entropy. That is
Yeah,
actually the entropy itself.
no, no, we have used this one, right? p minus p log of p, and I think minus 1 minus p.
That is entropy. It's not a cross entropy.
This was entropy, but it's kind of a similar formula here, right?
No, the cross entropy, you take the logarithm of not the label, but it is actually the probability. You take the probability log
Okay.
and multiply with the label.
Okay. Okay. That's okay. That is, but analogously, I would say this is the same, but it's okay.
It does. Of course, entropy remain the same.
Yeah. So okay, but the final thing is, let's say you can use this one, or actually you can use this one also. That is not the wrong thing. If your output prediction, right, it is between only 0 and -1. Uh, that is possible, I think, but I think it is not taught in our lectures. So we'll, let's say, go with this, right? The cross. This is the correct one. This is the correct cross entropy loss. Is minus y log of y hat and into 1 minus y into log of 1 minus hat. That is correct. And that is, this is the general formula for all the, let's say, for more than one classes or more than two classes, right? Okay. We don't have much, I think, in this.
No, wait a minute. This will result in 0 or 1, right?
Which one?
Your cross entropy will be always either, if you're talking about the labels,
okay,
it's going to be either 0, -1, or 1. Something like that.
How? So it will be 0 and 1 when you have y hat also between 0 and 1, right?
But yeah, y is, it's multiplied by y, right? Y is going to be 0 or 1.
So let's say y hat is, let's say, some probability, right? Anyway, this is the probability, right?
That's a probability. Then it is okay.
Yeah, if it is 0.6,
No,
or
that's okay. That's okay.
yeah, in case of ReLU, it will give some number. Maybe it is higher.
Okay. Yeah, as long as it takes the probability, then it is okay.
Yeah, if it is equal to 1 and 0, then yeah, that's correct. That has to. But generally, you have, if you use the sigmoid, right, it will give me the probabilities between 0 and 1. If you use, I think, ReLU, then it will be 0 and that number, right? Whatever the real number, I think, say, would say any real number, right? And take any real number. And I think only these two are there for in our syllabus. We don't have that softmax generally, but for output side of the classifications, softmax is used. You can actually, this is the information, you can use it in deep learning anyway. But yeah, this is what it is. Any doubts in this? You can actually may encounter a numerical problem over this. Okay, so if you can actually come up with some numericals, only this small, this neural network. Maybe number of neurons may be different, but only one input layer, one hidden layer, and one output layer.
Sir, I have a question on this neural network. I sent it in chat.
Yeah.
So how many topics are left?
This is over. This is over. For 11 and 12, it is over. Suppose we have a data set with 100 samples. Each sample is
X belongs to R50.
And okay, the same. Suppose further we use a neural network model with 3 hidden layers. 3 hidden layers are there. Okay, the first hidden layer contains 80 neurons. Okay, how many parameters does the first layer of neural networks have? Okay, so try and find it out.
Sir, I tried, but the answer is 40. I found out 4080, but the answer given in the portal is 4081.
Okay, we'll see now. So you have 100 samples, right? 100 samples, and each sample is R50, right?
Yes.
Okay. So yeah. So how many input? What? Okay. How many neurons will be there in input layer?
100.
100, right? So it will be x100, and then x2, and each of xy is in R50, correct? And how many hidden layers are there here in the first, or how many neurons are there in hidden layer? This is 80, right? 80. So
wait a minute.
Yeah.
First layer should be only the number of
samples or number of
features.
Features.
Sample is a sequence, right?
That is what. So I am just.
I know. So
No,
it
no, I'm
should not be
starting.
100. It should be 50.
Yes, that's what. I think we have discussed it, right? When we said about this neural network. So these are the features, right?
Sorry,
Example.
why 50? Why 50?
This should be what?
50 features, right?
These are the
One
features.
at a time. One at a time.
Correct. So you understand it.
Achha, for
So
each input, 50 features. So in the
every
first layer,
every time, yeah, every time it. So this first layer of the
No,
input.
I think you see it observes one, and then second
okay,
what comes afterwards. It's a sequentially input.
So this is your
So the
input,
number of data points doesn't make any difference in this.
yeah. Okay, okay.
right? So
I
these are
see.
the features, and now you do one thing. You just for one input, right?
One
Or
at a time.
for one sample, let's say, you have these features, and now you provide it to the 80 things, right? So whatever the I think it is 80 here, right? Neurons. So now you can calculate how many weights are there. So I think from each x1,
4,000.
okay, this is 80, right? For each of feature to this is we need 80, and how many 50 times, right? 4,000.
And bias he has given.
Bias, if it is there, then you'll have to add how many biases are there.
80?
Input does no, does it have input layer, does it have bias?
No. Input layer doesn't have any bias.
How many biases? Where it is given,
No,
assume each neuron has,
Input layer generally doesn't have any bias, I guess.
no,
each
it can,
neuron
right?
each neuron in the network has a bias.
Yeah. So it can have bias also, right?
So
Actually you can have x naught here as a bias.
So, like, what do I do? It was a numerical question. I need to type an answer.
Correct. So
Uh,
okay, in general, okay, it is already mentioned that each of the neuron have a bias size. So what is the bias? Okay, how many here? It will be 80 here, right? So it is
yes,
4,000 are the weights, right? Without the bias.
yes.
Then we'll have 80 biases here. So
Okay.
either if I assume that there is no bias here, but if this also is a neuron, right? So we can actually assume 50 also here, if more. I don't know what is the exact answer. So the answer
The
can be
answer is 4081.
81. So it is considering only one bias here in the.
So how do I understand like if I need to add bias or not?
Actually, see, here it will not. So these of neurons, right? It will not have biases. So in input, right? These are all features, right? For the input layer, only one bias is there, which is x naught. So okay, what is your linear equation? It is w1 x1 plus w2 x2, and like that
Sir,
up to w. Let's say 50. Yes.
the output will have any uh, bias,
So,
sir?
but input layer neurons doesn't have any bias, right?
Okay. So okay, I don't know whether that question. But see, in general, I will tell you. In general, I'm saying to you is that let's say it will have one bias here. Input layer will have one bias, and that bias is like you can think of that bias as another feature, right? So it will be a constant or so kind of an intercept, right? If you are learning any line, so it will have so mx plus c, right? Mx plus c. So this c is actually a bias, right? And in our course, I think we have learned any line only using a slope, because all of our lines they are actually going through the origin, right? We didn't consider the bias in that case. So bias in the neural network will be these actual features given to me plus the intercept, and intercept actually that will be a bias, but that bias is uh, in this case, right? It can be accommodated as x naught. So one bias will be accommodated in the input layer. Other than that, you can have the biases separately here while calculating. So that is given to your network, like depending on your network, how many biases are required. So for me, if I wanted to write the answer, right, so that will be like 80 into 54,000. Maybe I'll not consider this bias in the input layer. I'll
no, you
consider
should. You no, I think
it is not written, right?
no, it's not written. But then bias is a bias with a different weightages to all the 80 neurons. Okay, instead of taking it as a 50 features, you take it as a 51,
51.
and the 51st bias itself is a variable.
Yes, that is correct.
So that is why it becomes 4081.
But
For
that is,
each data point,
Wait,
we take a bias, right? You're
yeah,
saying that.
you know what I'm saying is there is a, for 50 features are coming from the data.
Yes.
Add a bias which is a variable.
Okay.
Now all of them 51 input goes to all the 80.
Yes.
So there will be 80 times 51 is the total weightages that you have got to figure out. In
So,
addition, the bias itself will be a variable. So the total
oh,
variable will be 4081.
4080, isn't it?
801. 81.
see the according to you, you're saying what you'll have.
No, what you wrote is right. Zero x0 is the bias.
Yeah, x0 is bias, right? So that
Correct?
is, but
That
it is not mentioned in the question. That's why I just removed it.
is
But
not.
generally, it has to be written here,
Yes.
and
Now
then
you have a, now you will have how many weightages?
yeah,
4080, right?
with that is 4080. Yes, correct.
Now the x0 is to be trained. That is not given the data. Correct? That's a bias that you are going to figure out. So in as a model, you have got to figure out what are the values for this 4081
Okay, yeah,
parameters.
that's correct. Yeah, that's correct. Yeah, yeah, got it. That's correct.
Up to 4080, I get it. After that, how this one?
No, the bias is not given, right? Bias doesn't come from the data, right?
So okay, yeah. So
That is what you are supposed to learn.
okay,
Basically,
we'll try
it
to
will be an average. It will
yeah.
be sort of an average that over the data point, it will probably keep accumulating there.
So try to understand this way. Let's say you have this mx plus c, right? You have this variable x, right? And you will have to learn this parameter, right? Or maybe you can say that wx plus c, or in this case, we'll write wx plus b. Correct, right? Is that correct? So let's say if this is a variable, you will learn what? You will learn this parameter w, plus you will learn this also, right? The intercept, let's say. Is that okay? Right. So let us say if it is b, this is b, right? So you will have from each of 50 to all 80, right? How many weightages are there? So let's say that is 50 into 80. That is how many? I think 4000. Correct, right? This is okay for all of you?
4080 is okay, sir.
No, okay, no, at least understand this, right? For 50 it is 4000. From this to all 80 it is how many? 80. So that is 4080, right?
Yes, sir.
And now I need to learn this also, right?
Okay, okay.
And that one is from this, because I don't know this also. And that is why
Okay.
it is 4081. That is what the explanation. So basically, you try to understand from this analogy that it is like a intercept, like slope intercept form, right? So there is a slope and there is an intercept, and you are actually learning these two both, right? These two both are the parameters, kind of like that. That is why it is 4081. uh, but I don't know whether we have sir has mentioned anywhere in the lectures in the neural networks also they have used bias or not, but generally it is used. Generally it is used in the neural network problem. Is that okay? Okay. So you understand this also, right? This part, uh, how to find out the weightages, and you can actually calculate it from there. I hope that is clear to all of you. And the previous session also, I think this bagging, overfitting, and this SVM. So you may encounter the numericals in case of random forest, AdaBoost, and this neural network, the simple neural network with one hidden layer, one input layer, and one output layer. You should understand the soft margin classifier, how this alphas, how this beta, and the C, right, and this W star, epsilon star, how they are interrelated to each other. What will happen if the values change? Is that okay? Okay, so shall we stop now?
So one last question I sent in chat. Could we discuss that?
Okay,
It's
let's.
regarding to this bias. Yeah.
So what's the percentage of week 1 to 8?
Yeah, yeah, okay. I'll talk about it. That also. Just give me a minute. What is where is the question? Yeah, this one. Consider a neural
Yeah.
network with the number of
Yeah. Yeah.
neurons in different layers. The number of neurons in different layers as mentioned in the below list. Okay, where is the list?
Yeah. Yeah, I'm sending. Sorry. Yeah.
Okay, these are the input layer, hidden layers like that. Huh?
Yes. Yes.
First one
Yes.
is
Yes.
the list correspond to input layer. The last is the output layer, and in between the number of hidden neurons. Okay, hidden layers are there. So three hidden layers, one input and one output. Assuming that there is a bias associated with each neuron, how many total parameters need to be computed? Okay, so if I use the same logic which I have used here, what do you think should be the answer?
I found out the answer to be 73.
And what is the correct answer? And how do you find it out? What is
So,
the process?
like, I
Yeah,
multiplied 5 into 5, then 5 plus 4, then 4 into 3, and then 3 plus 1, and then added all of them.
5 into 5. Okay, that
Yeah.
is okay. And
Then 5 into 4,
okay,
then 4 into 3,
okay.
then 3 into 1.
And where you consider the bias?
Yeah, and then add the number of neurons as the biases.
And then what was the final? Okay, I'll just calculate. You just tell me the exact correct answer. What is the correct answer?
The correct answer is 73.
So, and what you do is just follow the 3 plus.
What is the problem, Barbara? You not getting 73?
I'm getting, but I did this in graded assignment. So now this bias thing came, and now I'm a bit confused.
No, why it is confused? You don't consider bias in the input and you will get the answer.
So in this question, the previous question that we discussed, we did count a bias.
I think that was the exception. Usually for input, bias is not considered.
Okay,
I think they have specifically mentioned that's why it was considered. Otherwise, you should not consider.
okay. I'll
If
just
nothing is
draw a
mentioned, you should
diagram.
not consider.
See, in that question and this question, both have
Mhm.
this line, assume each neuron in the network has a bias. So how do I understand that, like, when to do that exception?
Okay, okay, just a minute. I'll just the
I don't know. I know. Usually, most of the questions you can
Yeah, me
answer.
too. I've seen that
Yeah,
the
you
input
can
layer
answer.
doesn't have
You
any
can answer
bias.
without considering bias in the input.
okay. No, input layer will have bias. That's not a problem. So I think the simpler diagram might be.
Actually, none of our examples,
Yeah,
questions,
you are
whatever
not
it is
there.
given,
Correct.
nowhere input you have got a bias.
Okay, so yeah, so let us
But
say.
this particular one, what Abra is telling, the detailed question, you are considering bias. So that's why he's getting,
So okay,
in any case, people will get puzzled because
is
most
this?
of the all the questions are without bias in the input, but this one is discussed with a
Yeah, that
bias
is
in the
okay.
input.
That is okay. So I think it's fine. I think it will not be an issue, right? I think you can actually go with
Sir,
this. So
maybe
here,
in that question we are considering the features, and here it is actually
no,
data set.
here, uh, is it like that? How come?
Because it is features, it carries a bias. Maybe I'm just guessing.
I think no, no, no. Everything it is like every time it is a feature, right? Okay, so you just see this diagram. It's a weight and height is a feature, right? In the input layer, weight and height is a feature. And how many parameters do we need to learn here? One, 2, 3, 4, 5, 6, and 7, 8, and 9, right? The biases are considered here, correct?
Hari ne সময় পায় না এখন ফোন করছি
Huh?
Okay.
Right, and now just look at this diagram. So this plus one is a bias, right? So plus one bias is considered here also. So in the layer one or input layer, and like that you can actually have the biases here. So now the output layer is not having bias, but so this is not like very hard and fast rule that we should use it or not use it. You can use it, you cannot use it, what you wanted to learn, right? It is basically based on that thing. So if you wanted a regression line, right, or regression output at this end, then I think you should
Sir,
have the intercept also, right?
sir, in the input layer, I have 5 neurons. So what does this mean? Like
Okay,
five?
okay. For simplicity, let's say you are going for the exam, right? I think, see, don't worry about all of this. It's actually the part of the deep learning thing, right? Uh, Let us say you can think of, let's say, for this particular question, right? You can actually consider what biases were. So how you calculated 73 is, like, say you just multiplied all the weights, and now how you have added those biases in the hidden layer.
Yeah, so except the input layer, I have added all the neurons.
Ah,
They add up to 13. So 60 plus 13, 73.
fine. You can go with that. That's fine. So that is not like wrong thing, right? What I'm saying is that, uh, but depending on what kind of architecture you're using, right? It is based on that basically.
But in real
You can
life,
actually
look,
embed.
real life
Yeah.
there is nothing. Everything has to have a bias because the
Uh,
real data is not going to be centered. You
Correct.
have to keep adjusting. You got it. Obviously,
Yeah,
bias
yeah,
will be
that's
there.
true.
It might probably we can make it zero.
Yes,
So
you can make it zero. Yes. So
we
if
can
you
also
have
make it
bias,
zero if you don't want it, right?
yeah, you learn it
Yeah.
and you can actually
So
make it zero. That is not a
I
problem
think
there.
we should not worry about bias being there.
Yeah.
Ideally, if you are asked to design a system, you should always assume a bias. That is the most
and,
robust.
and eventually it will learn, right?
Yeah, it
And the
will
model
learn.
will learn and it will give you zero
Yeah,
if
some
you want.
problems here, maybe for simplicity, probably somebody might say there is no bias, in which case problem no, it's easier. Otherwise, conceptually, we should be tuned to always have a bias. A line doesn't
Yeah,
have to
yeah.
pass through zero, right?
So in the input layer, I have 5 neurons
Yeah.
and I have one data point. So what happens to the data point? It goes to the 5 input neurons.
No, no, 1 minute. What did you say? You have a data point which
Yeah,
has how
I
many
have
features?
one data point. One data point, 10 features, for example.
10.
Okay. Yeah.
Right. Now, suppose the
And
output. No,
and
wait, wait. Now you are saying that output. Forget the neuron. Just to take the
yeah,
sum of or some combination, linear combination of these features gives you an output. Correct?
okay. Yeah.
Now, when all of them are zero, will the output be zero? Suppose all the
Zero,
features are zero.
zero in what?
If all the features are zero, your output need not be zero.
Yeah,
Correct?
it's not
That is the bias.
necessary. Yeah.
That is the bias. So when the 10 features are available, I add one more and I can modify that so that I meet the requirement that the fit, the curve fit, whatever you are fitting need not necessarily pass through zero. Otherwise, it has to pass through zero. Correct?
Hmm.
That is the key. So bias, it's just like it allows you to probably make an affine space because all the physical data, everything is going to be non-centered. Correct?
Hmm. Yeah, yeah.
Any data physically, there is no absolute zero. If I take the preference of the customer's profile per sale, any data I collect, it's not going to be average zero. Correct?
Yes, correct.
So then if I apply all along in the whole MLT, we've been learning everything using a linear space, vector space. Vector space must have a zero. Correct?
Correct.
It's not centered.
Yeah, yeah. It's not centered.
So it has to be all the time. Bias will be there. We may aim
Yeah.
out for the simple.
Bias has to be present. Yes.
We are for the calculation. Sometimes yes, probably we take it convenient to go ahead, but then don't expect when you come into the industry that you are biased now. No, I didn't study it. Bias will be there.
Hmm.
Y equal to mx plus c. Whatever he is told is the exact thing that the c will be there.
Bias for the entire input, right? One bias for the entire input.
Correct.
Yeah, one
Okay.
only, right?
One bias at the input stage.
Yes,
Actually,
yes.
every stage will have a bias. When you say hidden layer such as 80 neuron, there will be a bias for the next layer.
Oh, so
Uh,
okay. Each neuron has a bias and a
no,
layer also has a bias.
Not
each layer will have a bias.
not each neuron, right? So
Not
you
each
can
neuron.
have hidden neurons
Each
you
layer
can
will have.
to add. So hidden neuron you can add, but
Ah,
for the input layer you can actually have for
ideally,
all features is one.
yes. When you do a project and the time,
Yeah.
you probably will come up. Input stage is 50 to 50 features you are picking up. One bias 51. First layer is 80 neuron plus a bias. That bias will not have anything to do with the earlier layer. It
So
is
Okay.
that
an independent variable
number
itself.
of weights actually are going to
Correct,
increase,
correct.
right? So if you have one bias in the input layer, the number of weights will be increased based on the number of neurons in the hidden
Mm.
layer. That also you'll have to consider. And one more thing is you
Very
can
interesting.
have the different biases for each of the neuron also. But see, it's not like very that the way you are seeing this, like it's very simple neural network. It's not like that way it will work. You may encounter very deep neural networks, right? And that time it will be very clear. So right now it's not like, yeah, the understanding is input layer can have, right, and it must have actually.
Mm-hmm. Yeah,
That
yeah, it must have. It must have a bias then.
but for simplicity, for understanding purpose, we don't consider while doing the calculations here. At least for MLT, we don't have that big, big neural network. It's like very shallow neural network, and it's just to give the understanding of what is the neural network look like, right? Whether you
Mm-hmm.
can use it for classification or regression purposes. It's one of the algorithms you can say, fine.
Okay, okay, sir.
Yeah, okay. I think we should stop here. And the answer to your question is how much weightage should be there, right? So from week 9 to 12, you can consider the weightage of around 60%, right? Or 60 to 70%. And the remaining will be for week 1 to 8. Is that okay?
Okay, sir.
Yeah.
Thank you.
Okay. Thank you, guys.
Thank you, sir.
Yeah.
Thank you,
All
sir.
the
Thank
best.
you. Thank
Thank you,
you.
sir. Thank you.
Yeah. Bye.
Thank you, sir.
Thanks, sir.